The universe is a massive place filled with countless wonders and mysteries. From tiny particles to massive galaxies, it stretches beyond what we can fully understand. There are billions of galaxies, each containing millions or even billions of stars. These stars, along with their planets, form solar systems that drift through the universe. Join us as we embark on a journey through space, exploring the incredible wonders of the cosmos, from the familiar to the unknown. The Sun, a medium-sized yellow dwarf star, sits at the heart of our solar system, and its influence is paramount to life on Earth. This star, approximately 93 million miles away, produces energy through the process of nuclear fusion, where hydrogen atoms combine to form helium, releasing an immense amount of energy in the form of light and heat. This sunlight is the primary source of energy for nearly all life forms on Earth. Plants utilize this sunlight for photosynthesis, converting light energy into chemical energy and producing oxygen, a vital element for the survival of most life forms. Without the steady supply of solar energy, Earth's temperatures would plummet, oceans would freeze, and life as we know it would cease to exist. The sun's gravitational force also plays a crucial role in maintaining the stability of our solar system. Its massive gravitational pull keeps Earth and the other planets in their respective orbits, preventing them from drifting off into the icy realms of space. The Earth's orbit around the Sun, taking 1 year to complete, creates the cycles of seasons. These seasonal changes profoundly affect ecological systems and agricultural practices, allowing diverse life forms to flourish. Additionally, the Sun emits solar wind, a stream of charged particles which interacts with Earth's magnetic field, sometimes giving rise to stunning phenomena like the auroras. In these ways, the Sun is not just a glowing ball of gas, but a life-sustaining powerhouse intricately tied to Earth's ecological balance and the rhythms of life. The birth of our solar system began over 4.5 billion years ago within a vast molecular cloud composed of gas and dust. This cloud, primarily consisting of hydrogen and helium, with traces of heavier elements, was part of a nebula, a stellar nursery where stars and planetary systems are born. It all started when a section of this molecular cloud experienced a disturbance, possibly from a nearby supernova explosion, causing the cloud to collapse under its own gravity. As the cloud collapsed, it began to spin, forming a protostar at the center that would eventually ignite into our Sun. The surrounding material flattened into a protoplanetary disk due to the conservation of angular momentum. Within this disk, particles began to collide and stick together, gradually forming larger and larger clumps through a process known as accretion. These clumps became the building blocks of planets, known as planetesimals. Over time, these planetesimals further coalesced into protoplanets, which continued to grow by gathering more material through gravitational attraction. In the hotter inner regions near the protostar, only metallic and rocky materials could condense, leading to the formation of the terrestrial planets like Earth and Mars. Farther out, where it was cooler, gas giants such as Jupiter and Saturn, composed mainly of hydrogen and helium, were able to form. Beyond these giants, icy bodies and comets took shape. What started as a cloud of gas and dust thus evolved into our intricate solar system, a testament to the dynamic and transformative processes of the cosmos. Each planet in our solar system boasts distinct characteristics that make it unique, contributing to the diverse tapestry of our celestial neighborhood. Starting with Mercury, the closest planet to the Sun, it is a small rocky body characterized by extreme temperature fluctuations from scorching highs of nearly 800 degrees Fahrenheit during the day to frigid lows of minus 330 degrees Fahrenheit at night. Mercury has no atmosphere to moderate these temperatures, and is heavily cratered, much like our moon, indicating a geologically inactive surface. Venus, Earth's so-called sister planet, due to its similar size and structure, veers dramatically in its environmental conditions. Enveloped in thick clouds of sulfuric acid, it experiences surface temperatures around 900 degrees Fahrenheit, making it the hottest planet in our solar system. Venus exhibits a runaway greenhouse effect, where its dense carbon dioxide atmosphere traps heat. Unlike most planets, it rotates backward, causing the sun to rise in the west and set in the east. Earth, unique for its liquid water and abundant life, has a balanced climate system sustained by a mix of oceans, an atmosphere rich in nitrogen and oxygen, and a protective magnetic field. Mars, the red planet named for its iron oxide soil, features the tallest volcano in the solar system, Olympus Mons, and a canyon system, Valles Marineris, that dwarfs the Grand Canyon. Though barren, Mars has polar ice caps and signs that liquid water once flowed on its surface. Jupiter, the largest planet, is a gas giant with a composition mainly of hydrogen and helium. Its most distinctive feature is the Great Red Spot, a colossal storm larger than Earth that has persisted for centuries. Another gas giant, Saturn, is renowned for its magnificent ring system composed of ice and rock particles that orbit the planet. Uranus stands out for its extreme axial tilt, rotating on its side, which results in unique seasonal changes. It has a faint ring system and is known for its blue-green color due to methane in its atmosphere. Neptune, the outermost planet, has supersonic winds with speeds exceeding 1,200 miles per hour and a striking deep blue hue, also attributed to atmospheric methane. This distant world features dark storm spots similar to Jupiter's. Lastly, the dwarf planet Pluto, though reclassified, remains a compelling subject with its icy surface, heart-shaped glacier, and 5 known moons, including the sizable Charon. Each planet, with its particular attributes, adds a unique chapter to the solar system's story, illustrating the vast array of conditions and compositions possible within our cosmic backyard. The inner rocky planets, Mercury, Venus, Earth, and Mars, differ significantly from the outer gas giants, Jupiter, Saturn, Uranus, and Neptune, in several fundamental ways, notably in composition, structure, and atmospheric conditions. The rocky planets, also known as terrestrial planets, are composed primarily of silicate rocks and metals. They have solid, well-defined surfaces, with mountains, valleys, craters, and, in the case of Earth and Mars, evidence of volcanic activity and tectonics. Their atmospheres, when present, are thin relative to their size. For instance, Earth's atmosphere supports life, while Venus's thick toxic atmosphere is rich in carbon dioxide, creating a severe greenhouse effect. Contrastingly, the gas giants are predominantly composed of hydrogen and helium, lacking solid surfaces. Jupiter and Saturn, the 2 largest planets, have thick layers of gaseous atmosphere overlaying possible cores of rock and metal. Their atmospheres are filled with swirling clouds, storms, and in Jupiter's case, the famous Great Red Spot, a gigantic centuries-old storm system. These planets also have immense magnetic fields and numerous moons, with Jupiter hosting at least 79 and Saturn over 60. Both planets are surrounded by complex ring systems, though Saturn's rings are the most prominent and well-known. Uranus and Neptune, often referred to as ice giants because of their substantial frozen water, ammonia, and methane content, differ slightly from the larger gas giants. Uranus has the peculiar characteristic of rotating on its side, possibly due to a massive collision early in its history, and possesses faint rings and a cold blue-green appearance due to methane in its atmosphere. Neptune, The farthest planet is noted for its intense blue color and extremely dynamic weather, with storm systems like the Great Dark Spot. The inner rocky planets are small, dense, and have a solid crust, while the outer gas giants are massive, less dense, and primarily composed of gaseous and icy materials, lacking a solid surface. These distinctions highlight the diversity of planetary formation and the varying conditions that can arise within a single solar system. The moons of our solar system offer an extraordinary glimpse into a diversity of astronomical bodies, each with unique characteristics that make them significant. Europa, one of Jupiter's Galilean moons, stands out due to its potential for harboring life. Beneath its icy crust lies a subsurface ocean kept liquid by tidal heating from Jupiter's immense gravity. This ocean may contain more water than all of Earth's oceans combined, raising intriguing possibilities for astrobiology. On the other hand, Iwao, another of Jupiter's moons, is renowned for its intense volcanic activity. This is the most volcanically active body in the solar system, with eruptions that can shoot plumes of sulfur and sulfur dioxide hundreds of miles into space. Iwa's surface is a constantly changing landscape of sulfuric lavas and massive calderas, sculpted by the gravitational tug-of-war between Jupiter and its fellow Galilean moons, Europa and Ganymede. Speaking of Ganymede, it holds the title of the largest moon in the solar system, even surpassing the planet Mercury in size. Ganymede is unique due to its magnetic field, the only such field detected around a moon, which suggests a partially liquid iron sulfide core. This magnetic phenomenon contributes to Ganymede's auroras, akin to those on Earth but influenced by Jupiter's magnetic environment. Saturn's moon Titan is another standout, featuring a dense nitrogen-rich atmosphere, much like early Earth's. Titan's surface is shrouded in thick orange smog, hiding a complex world with lakes and rivers of liquid methane and ethane beneath its icy exterior. Titan is also believed to harbor a subsurface ocean of water mixed with ammonia, offering multiple avenues for potential biological activity. Titan's atmospheric and surface chemistry make it a prime target for future exploration in the quest to understand prebiotic conditions and the potential for life. Enceladus, another of Saturn's moons, has captured scientific fascination with its dramatic geysers that eject plumes of water vapor, ice particles, and organic compounds from its south polar region. These geysers suggest a subsurface ocean beneath its icy crust, making Enceladus a key focus in the search for extraterrestrial microbial life. The ejected material contributes to Saturn's E-ring and presents a unique opportunity to sample potentially habitable environments indirectly through space missions. Lastly, Neptune's moon Triton is notable for its retrograde orbit, indicating it may have been captured by Neptune's gravity rather than having formed in place. Triton has geysers that spew nitrogen gas, indicating subterranean activity. Its surface is a frozen reflective mix of water and nitrogen ice with cantaloupe terrain that puzzles scientists to this day. This combination of a retrograde orbit and surface activity makes Triton a compelling subject for studying the dynamics of captured celestial bodies. These moons showcase a magnificent variety of geologic, atmospheric, and potentially even biological phenomena, each contributing uniquely to our understanding of planetary science and the potential for life beyond Earth. The asteroid belt, located between the orbits of Mars and Jupiter, plays a fascinating and multifaceted role within our solar system, consisting of countless rocky bodies ranging from tiny dust particles to massive asteroids hundreds of miles in diameter. The belt is a region of leftover planetesimals that never coalesced into a planet. It's estimated that the total mass of all the objects in the belt is less than that of Earth's moon. This belt acts as a sort of cosmic dividing line, separating the inner rocky planets from the outer gas giants, and is believed to have formed from the primordial solar nebula under the influence of Jupiter's overwhelming gravity. One of the key influences of the asteroid belt is its impact on Earth's geological history. Occasionally, gravitational interactions, especially those involving Jupiter, can nudge asteroids out of their regular orbits, sending them careening toward the inner solar system as potential impactors. Such events have had profound effects on Earth, with the most famous example being the asteroid impact that contributed to the extinction of the dinosaurs 66 million years ago. These rogue asteroids can also offer valuable scientific insights when they are captured and studied, as they contain pristine material from the early solar system. Moreover, the asteroid belt serves as a natural laboratory for understanding the process of planetary formation and differentiation. Some of its largest inhabitants, like Ceres and Vesta, have been the focus of detailed studies. Ceres, classified as a dwarf planet, even shows signs of water ice and possible cryovolcanism, hinting at complex geological processes. Vesta, on the other hand, has a differentiated structure similar to that of terrestrial planets, with a core, mantle, and crust, indicating that it underwent internal melting at some point. Additionally, the asteroid belt acts as a source of potential resources for future space exploration. Elements like iron, nickel, and even water locked in the form of ice are found within these asteroids. Scientists and entrepreneurs have proposed ambitious plans for asteroid mining, which could provide materials essential for long-term human space missions and habitation, reducing the need to transport everything from Earth. Comets, often described as dirty snowballs, play a multifaceted and significant role in the solar system. Composed mainly of ice, dust, and organic compounds, comets originate from the distant icy regions of the solar system, primarily the Kuiper Belt and the Oort cloud. As they travel toward the sun, they undergo dramatic transformations that provide critical insights into the primordial conditions of our solar system. When a comet approaches the sun, the increasing heat causes sublimation of its ices, releasing gas and dust to form a glowing coma around the nucleus, and often spectacular tails that can stretch for millions of miles. One of the primary roles of comets is their pristine state as ancient relics. These icy bodies remain mostly unchanged since their formation over 4.5 billion years ago, acting as time capsules preserving information about the early solar system. By studying comets, scientists gain valuable clues about the composition of the solar nebula that gave birth to the planets. Notably, missions like the European Space Agency's Rosetta, which landed on Comet 67P, Churyumov-Gerasimenko, have provided unprecedented data, revealing complex organic molecules that could help us understand the building blocks of life. Comets have also significantly contributed to Earth's own history. It is hypothesized that comets played a crucial role in delivering water and organic molecules to the early Earth. This delivery system of crucial compounds may have been critical in the emergence of life. The isotopic similarities between Earth's water and water found in some comets bolster this theory, suggesting that cometary impacts in the young solar system helped seed our planet with the essential ingredients for life. Comets have a lasting influence on planetary atmospheres and geological history. Their impacts can be both beneficial and catastrophic. For example, comet impacts with Earth have been proposed to have caused significant atmospheric changes and may have been a factor in mass extinction events. The role of comets in distributing organic materials and water across the solar system, as well as their dynamic interactions with planetary bodies, underscores their importance in shaping the evolution of the solar system. Comets are not merely celestial wanderers, they are crucial to understanding the solar system's past, present, and future. They offer insights into the primitive materials from which planets formed, may have played a key role in delivering life's essential ingredients to Earth, and continue to influence the dynamics and chemistry of our planetary neighborhood. The Kuiper Belt and the Oort cloud significantly shape our understanding of the solar system's boundaries, acting as reservoirs for a myriad of icy bodies and providing clues about the solar system's formation and evolution. The Kuiper Belt, a disk-like region beyond Neptune's orbit, extends from about 30 to 50 astronomical units from the Sun. It contains thousands of small icy objects, including dwarf planets like Pluto, Haumea, and Makemake. The discovery of these objects, particularly since the late 20th century, has revolutionized our perspective on the solar system's outer regions, illustrating that the solar system is much more extensive and complex than previously thought. The Kuiper Belt is crucial for understanding the transition zone between the inner solar system, governed by the gravity of the major planets, and the more sparsely populated outer regions. The varied compositions and orbital dynamics of Kuiper Belt objects suggest that many have remained relatively unchanged since the solar system's early days, preserving pristine materials from the solar nebula. These objects provide valuable insights into the processes that governed planet formation and migration. Furthermore, the existence of structures like the scattered disk, an area with objects on even more extreme orbits extending well beyond the Kuiper Belt, hints at gravitational interactions with Neptune and other outer planets, shaping the present configuration of the solar system. Hypothetically, the Oort cloud, a vast sphere that may extend from about 2,000 to 100,000 astronomical units from the Sun, is believed to be the source of long-period comets, which have orbits lasting thousands to millions of years. Though no direct observations have been made due to its extreme distance, the Oort cloud remains a fundamental concept for explaining the origin of these long-period comets. Theoretical models suggest that the Oort cloud formed from remnants of the primordial disk of gas and dust that encircled the young Sun, with its objects being scattered to great distances by gravitational interactions with the giant planets and passing stars. The Oort cloud and Kuiper Belt collectively shape our understanding of where the solar system ends and interstellar space begins. They act as boundary markers that indicate the gravitational influence of the Sun extends far beyond the planets. Studying these distant regions helps us understand the solar system's formation, the migration of planets, and the gravitational interactions with nearby stars and the galactic environment. As such, the Kuiper Belt and Oort cloud not only define the outer edges of our solar system, but also serve as archives of its history and key elements in the broader context of astrobiological and planetary science. Pluto, once considered the ninth planet of our solar system before its reclassification as a dwarf planet in 2006, continues to fascinate scientists and the general public alike due to its unique, complex characteristics and the insights it provides into the outer reaches of our cosmic neighborhood. One of the most compelling aspects of Pluto is its dynamic geology. Unlike many bodies in the Kuiper Belt, Pluto is far from a cold, dead world. The data sent back by NASA's New Horizons mission in 2015 revealed a surprisingly varied surface, featuring vast plains of nitrogen ice, towering mountains of water ice, and evidence of recent geological activity. For instance, the heart-shaped plain called Sputnik Planitia is thought to be a gigantic, slowly convecting glacier of nitrogen ice situated within a vast basin likely created by an ancient impact. Adding to the intrigue, Pluto's atmosphere, though thin, is another remarkable feature, composed mainly of nitrogen, with traces of methane and carbon monoxide. This tenuous atmosphere undergoes seasonal changes, expanding and contracting as Pluto moves through its elongated orbit around the Sun. During the closest approach to the Sun, surface ice sublimates, replenishing the atmosphere, while it freezes back onto the surface as Pluto drifts away. Such dynamic changes are a testament to the complex interactions between surface and atmospheric processes, even on small, distant worlds. Pluto's system of moons also adds layers to its allure. Charon, Pluto's largest moon, is so substantial that the center of mass of the Pluto-Charon system lies outside the surface of Pluto itself, making it a binary system. Charon has its own puzzling geological features, including a colossal canyon system and a dark reddish area at its north pole, informally named Mordor Macula. This interplay between Pluto and Charon raises intriguing questions about tidal interactions and their shared evolutionary history. The smaller moons, Styx, Nix, Kerberos, and Hydra, exhibit chaotic rotations, likely influenced by the gravitational complexities within the Pluto-Charon system. Astrobiologically, Pluto tantalizes with the potential for chemical processes that could offer insights into fundamental organic chemistry. While it's unlikely to host life as we know it, due to its frigid temperatures, the organic molecules detected on its surface, produced by interactions of sunlight and cosmic rays with nitrogen and methane, are of great interest for understanding prebiotic chemistry in the solar system. Pluto's atmosphere, dynamic surface, complex geological history, and captivating moons continue to make it a subject of fascination, illustrating the unexpected complexity that small icy bodies can possess. Its study enriches our understanding of the diverse processes that govern planetary bodies, especially in the far reaches of our solar system, where the interplay of ices, geology, and atmospheric dynamics unfold in a distinctly different environment than that of the inner planets. Mercury, the innermost planet in our solar system, holds a trove of intriguing facts that captivate astronomers and enthusiasts alike. One of the most striking characteristics of Mercury is its extreme temperature variations. Due to its lack of a substantial atmosphere to retain heat, surface temperatures on Mercury vary dramatically. Daytime temperatures can soar to nearly 800 degrees Fahrenheit, while nighttime temperatures plunge to a frigid minus 330 degrees Fahrenheit. This stark contrast highlights the planet's exposure to the sun's intense heat and its inability to trap that heat once it retreats into night. Another fascinating feature of Mercury is its geological history, evidenced by its heavily cratered surface reminiscent of our moon. The Caloris Basin, one of the largest impact craters in the solar system, stretches over 960 miles in diameter and is a testament to the cataclysmic events in Mercury's past. Surrounding the basin are regions filled with chaotic terrain, believed to have been caused by the shock waves from the impact. Mercury's surface also features vast smooth plains thought to be ancient volcanic fields and enormous cliffs or scarps, some extending hundreds of miles long and rising over a mile high. These scarps likely resulted from the planet cooling and contracting over billions of years, causing the crust to buckle. Moreover, Mercury's core constitutes a significant portion of its interior, extending about 85% of the planet's radius, which is unusually large for a terrestrial planet. This iron-rich core generates a magnetic field, though it's only about 1% as strong as Earth's. The presence of a magnetic field indicates that Mercury's core is at least partially molten, and understanding its dynamics helps scientists learn more about planetary magnetism and thermal evolution. Despite its proximity to Earth, Mercury remains somewhat elusive, primarily due to its proximity to the Sun, making observations difficult. However, missions like NASA's MESSENGER, which orbited Mercury between 2011 and 2015, have vastly increased our knowledge about this small dynamic world. The data from MESSENGER revealed surprising details, such as the presence of water ice in permanently shadowed craters near Mercury's poles. These ice deposits, sheltered from the sun's rays, suggest the delivery of icy materials by comets or asteroids. Mercury's peculiar orbital characteristics also contribute to its intrigue. It has a highly elliptical orbit and completes an orbit around the Sun in just 88 Earth days. However, due to its 3-2 spin-orbit resonance, Mercury rotates 3 times on its axis for every 2 orbits it completes around the Sun. This results in an unusual day-night cycle, where one Mercury solar day, sunrise to sunrise, lasts approximately 176 Earth days. Mercury fascinates with its extreme temperature variations, geologically young features like vast volcanic plains and towering scarps, a disproportionately large core, water ice and shadowed craters, and peculiar orbital dynamics. These aspects, combined with the mysteries yet to be unraveled, make Mercury a compelling subject in the study of planetary science. Venus's extreme heat, making it the hottest planet in our solar system, is primarily due to its runaway greenhouse effect. This phenomenon occurs when a planet's atmosphere contains greenhouse gases in such high concentrations that they trap vast amounts of heat, leading to consistently elevated surface temperatures. Venus's atmosphere, composed mainly of carbon dioxide, about 96%, and thick clouds of sulfuric acid, plays a crucial role in this process. The greenhouse effect on Venus begins with solar radiation passing through its atmosphere and reaching the surface. When this solar energy is absorbed by the planet's surface, it is re-emitted as infrared radiation, heat. On Earth, some of this infrared radiation escapes back into space, but on Venus, the dense carbon dioxide atmosphere acts like a blanket, trapping the heat. The trapped heat continually warms the atmosphere and the surface. This creates a feedback loop. As the atmosphere gets hotter, it holds more heat, boosting the temperature further. As a result, Venus's average surface temperature soars to around 900 degrees Fahrenheit, surpassing even Mercury, which is closer to the Sun but lacks a similarly thick heat-trapping atmosphere. The extreme atmospheric pressure on Venus, about 92 times that of Earth at sea level, exacerbates the situation. This pressure forces the atmosphere to retain more heat and compounds the greenhouse effect. Additionally, the sulfuric acid clouds reflect sunlight, preventing the surface from cooling down through radiative loss. This reflective layer also scatters and diffuses visible light, ensuring that heat gets dispersed throughout the atmosphere more evenly. What makes Venus particularly intriguing is that it offers a stark warning of the potent effects of greenhouse gases. Scientists believe Venus might have had a more temperate climate in its distant past, potentially with liquid water on its surface. However, as solar radiation increased over time, it likely led to the evaporation of water, which in turn released more water vapor into the atmosphere, another potent greenhouse gas. This exacerbated the warming, leading to the evaporation of even more water and ultimately transforming Venus into the inferno we see today. Venus's status as the hottest planet is attributed to its thick carbon dioxide-rich atmosphere, which generates an extreme and self-perpetuating greenhouse effect. Understanding this process not only sheds light on the conditions on Venus, but also provides a crucial example of the impacts of greenhouse gases on planetary climates, illustrating the delicate balance required to maintain habitable conditions. Mars, often dubbed the Red Planet, boasts a variety of significant geological features that capture the imagination and scientific interest alike. The most prominent and well-known of these features is Olympus Mons, the tallest volcano in the solar system, standing at a staggering height of about 13.6 miles. Olympus Mons is nearly 3 times the height of Mount Everest. This shield volcano, analogous in structure to the Hawaiian Islands volcanoes, but far larger, showcases the immense scale of Martian geology. Another remarkable geological feature on Mars is the Valles Marineris, an extensive canyon system that stretches over 2,500 miles long and plunges depths of up to 4 miles. This colossal rift, which dwarfs Earth's Grand Canyon, is thought to have formed through a combination of tectonic activity and the surface collapsing due to the pulling apart of Mars's crust. The Valles Marineris offers invaluable insights into the tectonic forces that have shaped the Martian landscape, revealing a complex history of crustal movement and possible volcanic influences. Additionally, Mars is home to a variety of evidence of ancient water flows, particularly in the form of outflow channels and valley networks. These features suggest that liquid water once carved pathways across the planet's surface. For instance, Ares Vallis and Madam Vallis are extensive channels that likely formed from catastrophic floods, while valley networks like those seen in Nanidae Vallis hint at sustained surface water flow in Mars's distant past. These ancient waterways have fueled speculation and interest regarding the planet's potential to have once harbored life. Mars also features extensive plains, dune fields, and polar ice caps that grow and recede with the changing seasons. The vast northern plains, such as the Vestitus Borealis, are believed to be the remnants of ancient ocean beds. Meanwhile, the southern hemisphere is characterized by heavily cratered highlands that lend further evidence to Mars's dynamic and often violent history. The polar regions of Mars are particularly fascinating, as they consist of layers of water ice and carbon dioxide ice, which vary in thickness throughout seasonal cycles. These polar ice caps offer direct evidence of Martian climate change over geological time. Additionally, the presence of unique geological formations known as chaotic terrain adds to Mars's intrigue. These areas are characterized by randomly oriented large blocks of rock that appear to have been disrupted by some form of underground collapse, possibly due to the melting of subsurface ice. These geological features not only make Mars a captivating subject of study, but also provide essential clues about the planet's climatic and volcanic history, surface processes, and potential habitability. Each discovery, from towering volcanoes to ancient river valleys and mysterious chaotic terrains, enriches our understanding of Mars and its potential to have supported life, shaping the broader narrative of solar system exploration. Jupiter's atmosphere, a swirling cauldron of hydrogen, helium, ammonia, and other trace gases, is the birthplace of its iconic Great Red Spot, an immense, persistent anticyclonic storm. This storm, which has raged for at least 350 years and possibly much longer, is a striking testament to the dynamic processes at play in Jupiter's turbulent atmosphere. The Great Red Spot's origins and longevity are intertwined with Jupiter's unique atmospheric conditions. Jupiter's rapid rotation, completing one rotation every 10 hours, generates powerful east-west jet streams and creates bands of clouds that encircle the planet. These bands, known as zones and belts, move at different speeds and in opposite directions, creating shear zones where gases move violently against each other. The Great Red Spot is located in one of these shear zones, specifically between a westward moving belt and an eastward moving zone, fostering the storm's rotation. The storm itself is an anticyclone, which means that it rotates counterclockwise in the southern hemisphere and has a high-pressure core. Unlike cyclones on Earth, which generally weaken over time, Jupiter's Great Red Spot is fueled by constant energy from the planet's internal heat. Jupiter radiates more heat than it receives from the Sun. This internal heat powers the convection currents that drive the banded wind patterns and storms, thus feeding the Great Red Spot and contributing to its longevity. Moreover, the storm's deep roots extend far into the atmosphere, possibly as deep as 200 miles below the cloud tops, which adds to its stability. The distinctive red color of the Great Red Spot remains somewhat of a mystery, but it is believed to be caused by complex chemical reactions driven by solar ultraviolet radiation and the planet's atmospheric conditions. Compounds like ammonium hydrosulfide, possibly mixed with other chemicals like phosphorus or sulfur, may be responsible for the reddish hues. These compounds can undergo reactions in the turbulent, high-energy environment of Jupiter's upper atmosphere, giving the storm its striking appearance. The intensity of the red color can vary over time, suggesting changes in the chemical composition or the dynamics within the storm itself. In addition to its color and longevity, the Great Red Spot is of monumental size. It originally measured over 25,000 miles across, large enough to encompass 3 Earths side by side. However, it has been shrinking in recent decades and is now about 10,000 miles in diameter. Despite this reduction in size, the Great Red Spot remains the largest known storm in the solar system. Saturn's rings are one of the most stunning and distinctive features in our solar system, setting the planet apart with their immense size, brightness, and complexity. Unlike the ring systems of other gas giants, Jupiter, Uranus, and Neptune, Saturn's rings are extraordinarily prominent and easily visible even with small telescopes. These rings are composed primarily of countless particles of ice and rock, ranging in size from tiny grains to large boulders. One remarkable aspect of Saturn's rings is their sheer scale and structure. The rings extend up to 175,000 miles from the planet's equator, yet they are astonishingly thin relative to this vast width, with a thickness that varies from about 30 feet to several hundred feet. The rings are divided into 7 primary sections, labeled A through G, in order of their discovery, with the A, B, and C rings being the most prominent. These bands are separated by gaps such as the Cassini division, a 2,920-mile wide space between the A and B rings, where fewer particles reside due to gravitational interactions with Saturn's moons, particularly Mimas. Another feature that sets Saturn's rings apart is their vivid brightness. Composed largely of water ice, the rings reflect sunlight efficiently, contributing to their luminescent appearance when viewed from Earth. The high albedo reflectivity of the ice particles gives Saturn's rings a brilliant, almost ethereal look, in stark contrast to the darker, less prominent ring systems of the other gas giants. Moreover, Saturn's ring system exhibits dynamic behaviors and intricate patterns. Gravitational interactions with Saturn's numerous moons, over 80 have been identified, cause various effects, including the creation of ringlets, waves, and gaps within the rings. Some of Saturn's small moons, known as shepherd moons, play a crucial role in maintaining the sharp edges of the rings. For instance, the moons Prometheus and Pandora shepherd the F-ring, their gravitational influence corralling its particles and maintaining its narrow, braided structure. These gravitational interactions facilitate fascinating phenomena such as spiral density waves and bending waves, which propagate through the ring particles and offer insights into the physical principles governing disk systems in the universe, from planetary rings to protoplanetary disks around young stars. Another distinctive aspect is the seasonal changes observed in Saturn's rings, influenced by the planet's axial tilt of approximately 27 degrees. As Saturn orbits the Sun over its nearly 30-year-long period, the angle at which the rings are illuminated changes, leading to alternating periods of brilliant illumination and near invisibility. These changing perspectives allow for detailed studies of the ring particles' composition and structure from various angles. The enigmatic origin of Saturn's rings also adds to their uniqueness. While the precise mechanism that formed the rings remains uncertain, leading hypotheses include the disintegration of a comet, the breakup of an icy moon, or the remnants of the primordial disk from which Saturn formed. These theories suggest that the rings are relatively young, estimated to be less than 100 million years old, making them transient features on geological timescales. Saturn's rings captivate with their immense scale, brilliant brightness, intricate structures, and dynamic behaviors. These features, coupled with the fascinating gravitational interactions with Saturn's moons and the ongoing mystery of their origin, make Saturn's rings not only the most prominent, but also the most scientifically intriguing ring system in our solar system. Their study continues to enhance our understanding of planetary ring dynamics, the history of the Saturnian system, and the broader processes shaping disk systems in space. Imagine a planet spinning almost on its side, as if a hand reached out and flicked it like a top. This is Uranus, the seventh planet from the Sun, with an axial tilt of 98 degrees. Unlike Earth, which has a tilt of approximately 23.5 degrees, Uranus's extreme tilt causes it to experience the most severe seasons in the entire solar system. Picture this: for about 42 Earth years, one pole is plunged into a dark and frigid winter, while the opposite pole basks in continuous daylight. Then, during the planet's orbit of 84 Earth years, the roles gradually reverse, resulting in a dramatic exchange between deep freeze and relentless sunshine. The origins of this skewed axis are still a topic of much debate among astronomers. One prevailing hypothesis suggests a colossal collision with an Earth-sized object early in the planet's history. This cataclysmic impact likely knocked Uranus over, leaving it with its present peculiar orientation. Consequently, Uranus's extreme axial tilt sets the stage for drastically varying atmospheric conditions and peculiar weather patterns. Scientists believe that these seasons could stir up massive changes in the planet's atmospheric dynamics, potentially driving winds to supersonic speeds and creating complex cloud formations visible even from telescopes on Earth. These phenomena make Uranus an exciting subject for both amateur stargazers and seasoned planetary scientists, offering a cosmic dance of light and darkness that underscores the fragile and extraordinary nature of celestial mechanics. Neptune, the eighth and furthest known planet in our solar system, harbors some of the most astounding and potent weather phenomena observed, including winds that can reach up to 1,300 miles per hour. These supersonic winds, far exceeding the speed limits of hurricanes and typhoons on Earth, present one of the biggest mysteries about this distant blue giant. At such staggering velocities, Neptune's winds can strip clouds and churn gases in a spectacular ballet of atmospheric fury. Despite the planet's incredible distance from the Sun, which contributes to its frigid average temperature of around minus 373 degrees Fahrenheit, its atmosphere supports these relentless storms. The driving mechanisms behind Neptune's fierce winds remain an enigma. One leading theory proposes that the internal heat generated by the planet, surprisingly high given its location in the solar system, may set the stage for such dynamic weather. Neptune is believed to radiate more than double the energy it receives from the Sun, suggesting an internal heat source, possibly from the slow gravitational compression of its fluid interior. This internal heat might drive convection currents in the atmosphere, creating massive temperature differences that fuel violent storms and aggressive winds. Another puzzle is how these storms maintain their intensity without dissipating quickly. The Great Dark Spot, a massive storm system akin to Jupiter's Great Red Spot, provides an example of these intense and somewhat persistent weather patterns. These mysteries make Neptune a fascinating subject of study, as scientists use telescope observations and data from Voyager 2's flyby to unravel the forces at play in one of our solar system's most turbulent atmospheres. Exploring the vast expanse beyond our solar system, scientists have devised ingenious methods to study planets orbiting stars light years away, known as exoplanets. One of the most prominent techniques is the transit method, which takes advantage of the slight dimming of a star's light as a planet passes or transits in front of it. When this minuscule dip in brightness occurs at regular intervals, it indicates the presence of an exoplanet. Observatories like NASA's Kepler Space Telescope have famously utilized this method, leading to the discovery of thousands of exoplanets by monitoring numerous stars simultaneously for these tiny fluctuations. Another fascinating approach is the radial velocity method, often referred to as the wobble method. When a star has a planet orbiting it, the gravitational pull from the planet causes the star to move slightly in its own small orbit. This to and fro movement induces shifts in the star's light spectrum, observed as alternating blue and red shifts due to the Doppler effect. By meticulously tracking these spectral changes, astronomers can determine the planet's mass and its distance from the host star. Alongside these methods, direct imaging, though challenging due to the overwhelming brightness of stars compared to their planets, has achieved remarkable successes with advanced techniques like coronagraphy that block a star's light to reveal the faint glow of orbiting exoplanets. These methods collectively paint a richer picture of the cosmos, allowing scientists to infer the size, composition, and even atmospheric conditions of these distant worlds. While each method has its limitations and challenges, their combined data push the boundaries of our understanding, bringing us closer to answering profound questions about the potential for life and the diversity of planetary systems throughout the galaxy. Delving into the heart of our solar system, the Sun, we find it composed of several distinct layers, each playing a unique role in its structure and functioning. At the core lies the powerhouse of the Sun, where temperatures soar to around 15 million degrees Celsius. Here, nuclear fusion occurs, the process by which hydrogen atoms are converted into helium, releasing a staggering amount of energy in the form of light and heat. This energy takes thousands to millions of years to journey outward from the core, gradually moving through the radiative zone, where it is absorbed and re-emitted by atoms in a slow zigzag-like path. Surrounding the radiative zone is the convective zone, where the temperature drops enough for the energy to be transported by convection currents. Hot plasma rises towards the surface, cools, and then sinks back down to be reheated, creating a boiling, turbulent environment, reminiscent of a pot of soup on the stove. Above this, we find the Sun's visible surface, the photosphere, characterized by a relatively cooler temperature of about 5,500 degrees Celsius. This layer is where sunlight permeates into space, and it is also here that sunspots, cooler, magnetically active regions can be observed. Above the photosphere lies the chromosphere, a region seen during solar eclipses as a reddish glow, and further out is the corona, the sun's outermost layer. The corona is surprisingly hotter than the layers below, soaring to temperatures in the millions of degrees Celsius, a mystery that has intrigued scientists for years. It is in the corona that solar wind, the stream of charged particles released from the sun, originates, influencing space weather and impacting planets in the solar system, including Earth. Each layer of the sun, from its intensely energetic core to its outer corona, contributes to the dynamic processes that not only sustain the sun's radiant glow, but also profoundly affect the entire solar system. Nuclear fusion is the monumental process that powers the sun, transforming hydrogen into helium and unleashing vast amounts of energy that light and warm our entire solar system. Deep within the sun's core, where temperatures reach a blistering 15 million degrees Celsius and pressures are unimaginably intense, hydrogen nuclei overcome their mutual repulsive forces. These nuclei, composed of protons, collide with enough force to fuse together, forming helium nuclei in a series of steps known as the proton-proton chain reaction. During this fusion process, a tiny fraction of the mass of the hydrogen is converted into energy, as described by Einstein's iconic equation, E mem c quad t is. This equation highlights the profound concept that even a small amount of mass can be converted into a significant amount of energy. The energy produced in the core propagates outward, initially through the radiative zone, where it takes the form of photons that bounce between particles, slowly making their way towards the surface over thousands to millions of years. As the energy reaches the convective zone, it transfers through turbulent currents of hot plasma, rising and sinking, much like boiling water. Eventually, this energy emerges from the sun's outer layers, manifesting as the sunlight we receive on Earth. This process of nuclear fusion not only sustains the sun's radiance, but also creates the conditions for the synthesis of heavier elements as stars evolve. Larger stars fuse heavier elements, contributing to the cosmic abundance of elements essential for planets and life. Thus, nuclear fusion at the sun's core is not merely an energy generation mechanism, but a fundamental cosmic engine that influences the entire universe through the life cycle of stars. Fusion fosters the creation and dispersion of elements, intertwining the fate of distant galaxies with the atomic fabric of our very existence. This magnificent energy conversion process defines stars, drives their life cycles, and ultimately sows the seeds for a rich, element-diverse universe. Sunspots are fascinating features of the sun's photosphere, characterized by their relatively cooler temperatures and intense magnetic activity, typically appearing as dark patches against the sun's bright surface. Sunspots can vary in size, with some stretching over tens of thousands of kilometers, large enough to engulf Earth several times over. Sunspots form when intense magnetic fields emerge from the sun's interior, disrupting the usual convective processes and leading to regions with lower surface temperatures around 4,000 degrees Celsius compared to the surrounding areas that are about 5,500 degrees Celsius. The magnetic turmoil associated with sunspots often gives rise to dramatic solar phenomena such as solar flares and coronal mass ejections. Solar flares are sudden bursts of radiation caused by the release of magnetic energy, resulting in spectacular flashes of light, radio waves, and high-energy particles. When these flares erupt, they can accelerate protons and electrons to near-light speeds, contributing to space weather. Coronal mass ejections are even more substantial, involving the expulsion of huge quantities of the sun's plasma into space. When these charged particles travel toward Earth, they can interact with our planet's magnetosphere, leading to geomagnetic storms. These geomagnetic storms have numerous effects on space weather, influencing everything from satellite operations to communication systems and even power grids. High-energy particles from solar flares can damage satellite electronics, while the charged particles from coronal mass ejections can induce electric currents in power lines and pipelines on Earth, potentially causing outages and disruptions. Moreover, these interactions also cause the beautiful auroras, the northern and southern lights, as charged particles excite gases in Earth's upper atmosphere, creating shimmering curtains of light. Understanding sunspots and their influence on space weather is crucial in our technologically dependent world, providing insight to mitigate potential impacts on our modern infrastructure, and highlighting the dynamic relationship between our planet and its star. Solar flares and coronal mass ejections, two of the most powerful forms of solar activity, can have substantial impacts on Earth, both beautiful and hazardous. Solar flares are sudden, intense bursts of radiation emanating from the sun's atmosphere, driven by the complex interplay of magnetic fields around sunspots. These flares emit a vast array of electromagnetic radiation, including X-rays and ultraviolet light, which can reach Earth in just 8 minutes. When these high-energy emissions slam into Earth's atmosphere, they can disrupt the ionosphere, leading to disturbances in radio communications and navigation systems such as GPS. This is particularly crucial for aviation and maritime industries that rely on these systems for positioning and safety. Coronal mass ejections, on the other hand, are massive bursts of solar wind and magnetic fields rising above the solar corona and being released into space. When directed towards Earth, coronal mass ejections can take 1 to 3 days to arrive, carrying billions of tons of highly charged particles. Upon reaching Earth, these particles interact with our planet's magnetosphere, potentially triggering geomagnetic storms. These storms can induce electric currents in power lines, leading to transformer damage and widespread electrical grid failures, such as the notable blackout in Quebec, Canada, in 19. Additionally, coronal mass ejections pose significant risks to satellites, causing malfunctions or degradation of electronic components due to the intense particle radiation. Beyond the technological ramifications, solar flares and coronal mass ejections also paint the skies with the mesmerizing spectacle of auroras. When charged particles from these solar events collide with gases in the Earth's upper atmosphere, they excite the molecules, causing them to emit light and creating the northern and southern lights. These ethereal displays are visible closer to the poles, but can sometimes be seen at lower latitudes during particularly strong geomagnetic storms. While awe-inspiring, the dual nature of solar flares and coronal mass ejections as both potential threats to modern technology and as creators of natural beauty underscores the importance of monitoring and understanding solar activity to protect and prepare our technologically integrated society. The solar cycle, an approximately 11-year period during which the sun's magnetic activity waxes and wanes, profoundly influences solar phenomena and consequently space weather. This cycle is driven by the sun's dynamic magnetic field, which undergoes systematic changes in polarity about every 11 years. At the beginning of the cycle, known as the solar minimum, the sun is relatively calm, with few sunspots and minimal solar activity. As the cycle progresses towards its peak, the solar maximum, the number of sunspots increases dramatically, along with heightened instances of solar flares and coronal mass ejections. During solar maximum, the sun becomes a cauldron of activity, marked by the frequent emergence of new sunspots linked to robust magnetic fields. Solar flares, which are more common during this period, unleash bursts of radiation that can disrupt satellite communications, affect GPS systems, and interfere with power grids on Earth. Similarly, coronal mass ejections are more frequent and potent, potentially leading to severe geomagnetic storms when their charged particles collide with Earth's magnetosphere. These storms not only pose risks to our technological infrastructure, but also increase radiation exposure for astronauts and passengers on high-altitude flights over polar regions. The solar cycle fluctuations also exert a broader influence on space weather and near-Earth environmental conditions. For instance, increased solar activity during solar maximum can expand Earth's outer atmosphere, causing satellites to encounter more atmospheric drag, which can alter their orbits and require recalibration. Additionally, the sunspot cycle impacts the amount of ultraviolet and X-ray radiation reaching Earth, which can in turn affect the ozone layer and atmospheric chemistry. Understanding the solar cycle is crucial for predicting and preparing for these varying levels of solar activity. With advanced monitoring from observatories like NASA's Solar Dynamics Observatory and the European Space Agency's Solar and Heliospheric Observatory, scientists are better equipped to anticipate and mitigate the impacts of the sun's dynamic behavior on our increasingly technology-dependent world. Scientists employ a combination of solar observatories, satellites, and spacecraft to investigate the sun, unraveling the complexities of our star's behavior and its effects on the solar system. Ground-based solar observatories like the Daniel K. Inouye Solar Telescope in Hawaii provide unprecedented high-resolution images of the sun's surface, allowing researchers to study sunspots, solar flares, and other surface phenomena in meticulous detail. These telescopes utilize advanced optics and adaptive technologies to counteract Earth's atmospheric distortions, giving scientists a clearer view of the intricate dance of magnetic fields and plasma on the sun's photosphere. Complementing ground-based observations, space-based telescopes and probes offer unique perspectives free from atmospheric interference. NASA's Solar Dynamics Observatory, for instance, continuously monitors the sun in multiple wavelengths from extreme ultraviolet to visible light, revealing the dynamic processes occurring in the sun's outer layers. The Solar Dynamics Observatory captures detailed images of solar flares, sunspots, and magnetic field variations, providing crucial data to understand solar activity cycles and predict space weather events. Similarly, the European Space Agency's Solar and Heliospheric Observatory, operational since 1995, has been instrumental in monitoring the sun's atmosphere and detecting early signs of coronal mass ejections. Taking exploration even further, missions like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are designed to venture near the sun, gathering unprecedented close-up data. The Parker Solar Probe, launched in 2018, dives into the sun's outer corona where it withstands extreme heat while measuring magnetic fields, solar wind, and energetic particles. Its mission aims to shed light on the mysterious heating of the solar corona and the mechanisms driving the solar wind. Solar Orbiter, with its suite of instruments, performs close-range observations and takes high-resolution images of the sun's poles, regions previously difficult to study. By combining data from these various platforms, scientists create a comprehensive and dynamic picture of solar activity, helping to predict and mitigate the impacts of solar events on Earth's technological infrastructure and human activities. The moon's phases are a captivating dance of light and shadow, changing its appearance as it orbits around Earth. completing a cycle approximately every 29.5 days. This cycle, known as a lunation, results from the interplay between the positions of the moon, Earth, and the sun. As the moon orbits Earth, different portions of its sunlit side become visible to us, creating its various phases. These phases can be divided into 8 distinct stages. The cycle begins with the new moon, when the moon is positioned between Earth and the sun. During this phase, the side of the moon that faces Earth is entirely in shadow, rendering it invisible in the night sky. As the moon continues its orbit, it enters the waxing crescent phase, where a sliver of the moon's surface starts to be illuminated by the sun, forming a crescent shape. This crescent grows larger each night until the moon reaches the first quarter phase, often called a half moon, where half of the moon's disk is illuminated and visible from Earth. While the giant impact hypothesis remains the most widely accepted explanation, it continues to evolve with new data and improved computer simulations. Recent findings from lunar rock samples and advanced modeling suggest multiple such impacts could have contributed to the moon's formation. As lunar exploration continues, particularly with missions like NASA's Artemis program aiming to return people to the moon, scientists anticipate gathering more evidence to refine our understanding of this cosmic event. The study of the moon's origin not only illuminates the early history of our planet and its satellite, but also provides key insights into the processes that shape planetary systems throughout the universe. The moon's surface is a fascinating tapestry of geological features that narrate a history of intense celestial activity. One of the most striking features are the lunar maria, or seas, vast dark plains formed by ancient volcanic eruptions. Contrary to their name, these seas are not filled with water, but are expansive basaltic plains, created billions of years ago when molten lava flowed and solidified. Notable maria include Mare Tranquillitatis, Sea of Tranquility, and Mare Imbrium, Sea of Rains, sites that are easily visible to the naked eye as dark splotches on the moon's face. In stark contrast to the smooth maria are the lunar highlands, lighter in appearance and heavily cratered, forming the oldest parts of the moon's surface. These highlands are covered with impact craters of all sizes, a testament to the moon's turbulent past bombarded by meteoroids and asteroids. The largest of these craters, the South Pole Aitken Basin, spans about 2,500 kilometers and plunges to depths of 8 kilometers, making it one of the biggest impact structures in the solar system. Other well-known craters, such as Tycho and Copernicus, have distinctive central peaks and radiate bright streaks or rays of ejected material stretched out across the lunar surface. Another notable feature is the presence of lunar rills, which are long, narrow depressions resembling channels or valleys that can extend for hundreds of kilometers. These are believed to be the remnants of ancient lava flows or collapsed lava tubes. The moon also hosts scarps, cliff-like features that suggest tectonic activity, even though the moon lacks active plate tectonics like Earth. Scarps, such as the ones observed in the region called Rups Recta, the Straight Wall, indicate that the moon's interior is still cooling and contracting, causing the crust to crack and shift. The finer details of the moon's surface include its regolith, a layer of loose fragmented rock and dust generated by eons of micrometeoroid impacts. This powdery layer covers the moon's solid bedrock, creating a landscape of stark beauty and scientific interest. The combination of maria, highlands, craters, rills, scarps, and the ubiquitous regolith paints a vivid picture of the moon's geologic history, a silent witness to the dynamic processes that have shaped our closest celestial neighbor. The moon plays a crucial role in regulating Earth's tides through its gravitational pull. This gravitational interaction between the Earth and the Moon generates tidal forces that cause the ocean's water level to rise and fall in a rhythmic pattern. The most straightforward way to visualize this is to imagine the Earth as a massive sphere enveloped by a free-flowing shell of water. The gravitational attraction of the Moon pulls on this water, creating what is known as the tidal bulge on the side of Earth facing the Moon. The water bulges out towards it, creating a high tide. Simultaneously, on the opposite side of the Earth, inertia causes a second bulge, forming another high tide. As the Earth rotates, different areas pass through these bulges, experiencing high and low tides roughly twice a day. However, the situation is slightly more complex due to the alignment of the Sun, the Moon, and Earth, which can either amplify or moderate these tides. When the Sun, Moon, and Earth are in a straight line, such as during full moons and new moons, their combined gravitational forces produce more extreme tides, known as spring tides. During these periods, high tides are exceptionally high, and low tides are especially low due to the additive effect of solar and lunar gravitational pulls. Conversely, when the Sun and Moon are at right angles relative to Earth during the first and third quarters of the lunar cycle, their gravitational forces partially cancel each other out, resulting in neap tides, which are less extreme. The Moon's influence on tides also has larger impacts on Earth's natural systems and human activities. Tidal movements help facilitate the mixing of ocean waters, which is essential for distributing nutrients and sustaining marine life. For human civilizations, tides have historically been important for navigation, fishing, and even influencing coastal settlement patterns. Additionally, the interaction between the ocean tides and Earth's rotation exerts a braking force, gradually slowing Earth's spin and causing the day to lengthen over geological timescales. This interplay of gravitational forces and rotational dynamics elegantly demonstrates the Moon's significant, albeit often subtle, influence on our planet, tying the rhythms of the Earth intrinsically to its celestial companion. The Apollo moon missions, which spanned from 1969 to 1972, provided a treasure trove of scientific insights and technological advancements that have profoundly shaped our understanding of the Moon and influenced space exploration. One of the most significant achievements was the collection of approximately 842 pounds of lunar rocks, soil, and core samples. These lunar materials, meticulously examined back on Earth, revealed critical information about the Moon's composition, geological history, and the processes that have shaped its surface. Studies of these samples indicated that the Moon is composed primarily of silicate minerals, much like the Earth's mantle, lending support to the giant impact hypothesis of its formation. The Apollo missions also provided direct geological assessments through astronaut-led fieldwork on the Moon's surface. Astronauts performed experiments, deployed scientific instruments, and collected samples from diverse locations, including Highlands and Maria, which allowed scientists to piece together a comprehensive geological timeline. They discovered evidence of volcanic activity and impact cratering, showing the Moon's surface had been shaped by both internal processes and external bombardments. The deployment of the lunar module seismometers revealed moonquakes, offering insights into its internal structure. While the Moon lacks tectonic plates, the data suggested that it has a differentiated interior with a crust, mantle, and small core. Additionally, the Apollo missions pioneered numerous technological advancements, from spacecraft design to life support systems, and provided invaluable experience in extraterrestrial exploration. Technologies developed for these missions have had lasting impacts beyond space exploration, influencing everything from materials science to computer technology. The missions also fostered international collaboration and inspired generations of scientists, engineers, and the general public. The legacy of the Apollo missions extends to current and future lunar explorations. Instruments and techniques developed during these missions have set the foundation for modern lunar science. As humanity looks towards returning to the moon with programs like NASA's Artemis, aiming to establish a sustainable human presence on the lunar surface, the knowledge and experience gained from Apollo serve as guiding beacons. These missions not only underscored human ingenuity, but also cemented our place in the cosmos, proving that exploration and scientific inquiry can yield profound, world-changing insights. The future of human exploration and colonization of the moon is poised to be transformative, driven by advancements in technology, international collaboration, and ambitious space programs. One of the most significant initiatives in this arena is NASA's Artemis program, which aims not only to return humans to the moon by the mid-2020s, but also to establish a sustainable presence by the end of the decade. This program marks a bold step towards long-term lunar exploration, building on the legacy of the Apollo missions while leveraging modern technology and engineering. Artemis I, an uncrewed mission, will test the Space Launch System rocket and Orion spacecraft, setting the stage for subsequent crewed missions. Artemis I will follow with a crewed flyby, progressively leading to Artemis III, where astronauts will land on the lunar South Pole, a region rich in water ice and scientific potential. Beyond NASA's efforts, international and private sector involvement are crucial components of the new era of lunar exploration. The European Space Agency, Russian Space Agency Roscosmos, and China National Space Administration have all articulated plans for lunar missions, aiming to contribute to the collective scientific and exploratory goals. The International Lunar Research Station, a concept being developed by China and Russia, exemplifies this collaborative approach, envisioning a research outpost staffed by astronauts and robotic systems. Critical to the future of lunar colonization are the advancements in situ resource utilization. This involves harnessing the moon's natural resources, such as extracting water from lunar ice to produce oxygen and fuel, which will be vital for maintaining outposts and supporting further space endeavors. Infrastructure development will focus on building habitats that can shield astronauts from the harsh lunar environment, which includes extreme temperatures and harmful solar radiation. Innovations in habitat construction, potentially using 3D printing technology with lunar regolith, are already being explored. Commercial entities like SpaceX and Blue Origin are also pivotal to the lunar vision. SpaceX's Starship aims to transport large payloads and crew to the moon, significantly lowering the cost per launch and enabling more extensive missions. Blue Origin's Blue Moon lander is designed to facilitate cargo and crew transport, supporting the broader goals of lunar colonization. Through these collective efforts, the moon is set to become a hub for scientific research, technological innovation, and an essential stepping stone for deeper space exploration, such as missions to Mars. Establishing a human presence on the moon will provide invaluable experience in living and working in extraterrestrial environments, preparing humanity for the challenges and opportunities of a multiplanetary future. The vision for the moon is no longer a distant dream, but an emerging reality that could redefine our understanding of the solar system. Stars come in a bewildering variety of sizes, colors, and types, each telling its own unique story through the cosmos. At one end of the stellar spectrum are the diminutive yet abundant red dwarfs. These small stars, often less than half the mass of our Sun, burn their fuel so frugally that they can live for trillions of years, far outlasting stars like our own. With surface temperatures ranging between 3,000 and 4,000 Kelvin, red dwarfs emit a cool reddish light. Their energy efficiency and longevity contrast starkly with the more massive variants on the celestial stage. Moving up the scale, the Sun itself is a G-type main sequence star, often referred to as a yellow dwarf. Despite the seemingly modest designation, the Sun is actually quite large and luminous compared to many stars in the galaxy. Beyond it, we encounter the massive blue giants and the even more colossal blue supergiants. These luminous titans, like Rigel and Betelgeuse in the Orion constellation, are of particular interest, with surface temperatures soaring from 10,000 to over 30,000 Kelvin. These stars shine brilliantly in blue and white hues. However, their grandeur comes at a cost. Blue supergiants blaze through their nuclear fuel at an astonishing rate, which significantly shortens their lifespans to just a few million years. In the climax of their lives, many end in catastrophic supernova explosions, leaving behind enigmatic remnants such as neutron stars or black holes, the ultimate celestial mysteries. The birth of stars is a symphony of cosmic forces playing out in the dark, cold regions of space, known as stellar nurseries. These nurseries are vast clouds of gas and dust, predominantly composed of hydrogen and helium, drifting silently in the galactic arms. Over time, gravitational forces cause pockets of these clouds to contract and clump together. As these clumps grow denser, they begin to gather more material, and the temperature in the core rises. This continues until the temperature reaches about 10 million Kelvin. That's when nuclear fusion ignites, marking the birth of a new star. It's fascinating to think that the process starts so quietly, with mere whispers of gravitational attraction, and ends with the roar of nuclear fire. As the newly formed star gathers material, it often creates spectacular visual phenomena. Surrounding the young star, the leftover gas and dust form protoplanetary disks that may eventually coalesce into planets. In regions like the Orion Nebula, astronomical observations have captured the breathtaking beauty of these stellar birthplaces, where dense pillars of gas and dust spiral around infant stars, illuminated by their nascent light. The interplay of radiation pressure from the young stars and the gravitational tug-of-war creates intricate and ephemeral structures in the nebula. This awe-inspiring process, lasting millions of years, is a testament to the incredible forces at work in the universe, ensuring the cycle of star birth continues unabated, populating the cosmos with new sources of light and energy. The life cycle of a star is a grand narrative of cosmic proportions, woven through billions of years of dynamic changes. It all begins in stellar nurseries, vast clouds of gas and dust scattered throughout galaxies. As these clouds contract due to gravitational forces, protostars form and eventually ignite nuclear fusion in their cores, officially becoming main sequence stars. This stage, where stars spend the majority of their lives, is governed by a delicate balance between gravity pulling inwards and the outward pressure from nuclear fusion. Our Sun, for instance, has been in this stable phase for about 4.6 billion years, and is expected to remain so for another 5 billion years. As stars exhaust their hydrogen fuel, their fates diverge based on their initial mass. Stars similar in size to our Sun swell into red giants. In this expanded state, the outer layers are shed off, creating beautiful planetary nebula, leaving behind a dense hot core known as a white dwarf. These white dwarfs gradually cool and fade over billions of years. In contrast, massive stars experience more dramatic endings. After burning through heavier elements like helium, carbon, and finally iron, their cores collapse under gravity's relentless pull, triggering supernova explosions. This cataclysmic event can outshine entire galaxies temporarily, dispersing enriched material back into space, seeding future stellar generations. The remnants of these behemoth stars can form dense neutron stars, or if massive enough, collapse further into black holes, enigmatic points where gravity is so intense that not even light can escape. Thus, the life cycle of a star is a compelling tale of creation, transformation, and sometimes spectacular destruction, contributing continuously to the evolution of the universe. Supernovae, the titanic explosions signaling the death of massive stars, are not merely destructive events, they are also the architects of cosmic rebirth. When a supernova occurs, it releases an immense amount of energy, scattering the star's outer layers into the surrounding interstellar medium. This expelled material is rich in heavy elements like iron, oxygen, and silicon, elements forged in the star's core through nuclear fusion processes. These enriched clouds, known as supernova remnants, infuse the galaxy with essential building blocks that were previously locked within the star. The shock wave produced by the supernova also plays a crucial role in the birth of new stars. As it propagates through the interstellar medium, it compresses nearby clouds of gas and dust, instigating gravitationally bound regions that may collapse and form new stars. Interestingly, this process acts as a cosmic catalyst, enhancing star formation in surrounding regions of the galaxy. Areas rich in supernova remnants become fertile grounds for stellar nurseries. The Orion Nebula, for instance, showcases this beautifully, where regions dense with the remnants of past star deaths are now aglow with the light of emerging stars. This continuous cycle of death and rebirth, spurred on by supernova, ensures the cosmos remains a dynamic, ever-evolving tapestry where the end of one stellar life seeds the beginning of countless others. Black holes, often conjured in the imagination as voracious gravitational monsters, are the enigmatic remnants of some of the universe's most massive stars. They emerge from the violent end stages of stellar evolution, particularly through the grand finale of a supernova. When a star with a mass exceeding about 20 times that of our Sun exhausts its nuclear fuel, it can no longer hold off the relentless pull of gravity. The star's core collapses under its own weight, compressing its matter to a point of infinite density known as a singularity. Modern astronomy has codified 88 constellations, defining clear boundaries to aid scientific observations and catalog celestial objects. The International Astronomical Union formalized these boundaries in the 20th century, ensuring that every part of the sky belongs to a particular constellation. Today, while constellations continue to captivate our imagination and inspire awe, they also possess educational value, serving as mnemonic devices to locate stars, nebulas, and galaxies. Through the lens of history and science, constellations reveal the profound human desire to impose order on the cosmos and find meaning amidst the stars. Among the vast tapestry of stars lighting up the night sky, a few constellations stand out both for their striking patterns and the rich myths surrounding them. Take Orion, for example, one of the most recognizable constellations due to its prominent belt of three aligned stars. In Greek mythology, Orion was a mighty hunter, said to be so handsome and skillful that he caught the eye of the gods. This prowess eventually led to his tragic demise, either by the sting of a giant scorpion, captured as the constellation Scorpius, or through other mythic tales involving divine retribution. Regardless of the story's details, the epic heroism of Orion continues to captivate stargazers worldwide. Another constellation with a storied past is Ursa Major, known commonly as the Big Dipper in the Northern Hemisphere. The seven bright stars comprising the Big Dipper form part of a larger pattern resembling a great bear. Native American folklore often views the Big Dipper as a celestial bear pursued by three hunters, reminiscent of tales passed down through generations. Ancient Greek myths offer a different perspective, portraying Ursa Major as Callisto, a nymph transformed into a bear by a jealous Hera, only to be placed among the stars by Zeus. Her son Arcas forms Ursa Minor, the little bear, and together these constellations remain skybound symbols of mythic transformation and familial bonds. Cassiopeia, with its distinctive W shape, tells the tale of a queen whose vanity led to her downfall. According to Greek mythology, Cassiopeia boasted about her unrivaled beauty, claiming it even surpassed the Nereids, sea nymphs who were close to Poseidon, the god of the sea. In retribution, Poseidon condemned Cassiopeia to the night sky, forever spinning around the celestial pole on her throne, often appearing upside down, a constant reminder of her hubris. These constellations, along with others like Pegasus, Andromeda, and Leo, weave a rich tapestry of stories that blend cultural heritage, natural observation, and the timeless human penchant for storytelling, ensuring their legacy in both the annals of astronomy and mythology. The Milky Way galaxy, our cosmic home, is a vast spiraling assembly of stars, gas, dust, and dark matter, intricately structured into several distinct components. At the heart of the galaxy lies the galactic center, a densely packed region dominated by a supermassive black hole known as Sagittarius A3, which has a mass of about 4 million times that of our Sun. Surrounding this tumultuous core is the galactic bulge, a spherical collection of old stars and star clusters that stretches for thousands of light years. Extending outward from the bulge are the galaxy's most defining features: its spiral arms. These arms, named for their elegant sweeping curves, are regions of intense star formation. Our own solar system resides in the Orion Arm, a minor arm situated between the larger Perseus and Sagittarius arms. The arms are composed of young luminous stars and interstellar material, creating a glittering backdrop of stellar nurseries and nebulous clouds. The spiral structure is maintained by density waves that move through the galaxy, compressing gas and triggering new star formation as they pass. Encasing the spiral arms is the galactic disk, a thin, rotationally flattened plane containing most of the galaxy's stars and nebulae. The disk is enveloped by an extensive, diffuse halo of ancient stars and globular clusters, some of which are among the oldest known objects in the universe. This halo is also thought to be rich in dark matter, an elusive substance that exerts gravitational forces but emits no light, influencing the galaxy's overall mass and rotation. Beyond the halo lies the outer reaches of the galaxy, where solitary stars and faint streams of stars, remnants of past galactic mergers, wander in a sparsely populated expanse. The Milky Way's dynamic structure reflects a long history of interactions with other galaxies, shaping its evolution over billions of years. This grand, spiraling city of stars, stretching over 100,000 light-years in diameter, provides a celestial home for countless star systems, including our own, weaving the intricate fabric of our galaxy's identity. Galaxies, the colossal structures that compose our universe, can be classified into several distinct types based on their shapes and compositions: spiral, elliptical, and irregular. Each type offers unique insights into the processes of cosmic formation and evolution. Spiral galaxies, such as our Milky Way, are perhaps the most visually striking, with their graceful, winding arms extending from a central bulge. These arms are cradles of active star formation, giving rise to young hot blue stars that illuminate the spiral's grand design. Spiral galaxies can be further subdivided into barred and unbarred spirals, depending on whether a bar-like structure of stars cuts through the central bulge. The star populations within spiral galaxies are diverse, with older, redder stars predominantly populating the central bulge, and younger stars scattered throughout the arms. The well-defined structure indicates ongoing rotational motion and a rich supply of interstellar gas and dust essential for new star birth. Elliptical galaxies, in stark contrast, exhibit a more uniform oval-like shape and lack the complex structure seen in spirals. They range from nearly spherical to highly elongated forms and are often populated by older red stars. This aged star population suggests that elliptical galaxies have exhausted much of their interstellar gas, leaving minimal material for new star formation. Consequently, they are often quiescent and less active than their spiral counterparts. Elliptical galaxies are thought to form through the collisions and mergers of smaller galaxies, which can disrupt their initial structure and lead to the more homogeneous appearance observed today. Irregular galaxies deviate from these orderly schemes and lack a definitive shape. They are typically smaller than spiral and elliptical galaxies, and often appear chaotic in structure, with regions of active star formation interspersed among areas containing older stars. This irregularity can result from gravitational interactions with nearby galaxies or the remnants of galactic collisions. Their diverse appearances reflect a turbulent history, and they often contain significant amounts of gas and dust, fueling continuous star formation. These three types of galaxies, spiral, elliptical, and irregular, highlight the variety of forms and evolutionary paths cosmic structures can take. Spiral galaxies with their majestic arms and dynamic star formation, elliptical galaxies with their more settled, ancient populations, and the unpredictable, irregular galaxies each contribute to the rich tapestry of the universe, revealing the breadth of galactic architectures and their transformative histories. In the grand expanse of the universe, certain galaxies stand out for their sheer size, dwarfing even our Milky Way. Among these colossal structures, the largest known galaxy is IC 1101, a giant elliptical galaxy situated more than 1 billion light-years away in the constellation Virgo. IC 1101 spans an incredible 6 million light-years across, which is approximately 60 times the diameter of the Milky Way. This gargantuan galaxy is home to hundreds of trillions of stars, many of which are old and red, indicative of a galaxy that has long since ceased active star formation. Its monumental size is a result of numerous galactic mergers over billions of years, steadily accumulating mass and dimensions through gravitational interactions. Another awe-inspiring giant is ESO 306117, an elliptical galaxy located about 500 million light-years away. While not as vast as IC 1101, ESO 306117 still stretches over 1 million light-years in diameter. The presence of a vast number of globular clusters surrounding such massive elliptical galaxies suggests their complex and violent formative histories, often marked by frequent mergers and interactions with neighboring galaxies, further extending our understanding of cosmic giants. Furthering our understanding is the galaxy cluster Abell 2029, anchored by the massive elliptical galaxy NGC 6166. Although not as expansive as IC 1101, NGC 6166 is of significant interest due to its enormous central black hole and powerful radio emissions. This galaxy forms the core of one of the largest known galaxy clusters, contributing to its substantial gravitational footprint and the intricate dynamics of galaxy clustering. These galaxies, with their immense scale and rich histories, offer tantalizing glimpses into the processes driving galaxy evolution in the universe. By studying these cosmic leviathans, astronomers glean insights into the growth mechanisms of galaxies, the role of dark matter in shaping their structures, and the consequences of galactic mergers. Each of these giants serves as a testament to the boundless creativity and complexity inherent in the cosmos. The formation and evolution of galaxies are processes governed by a series of intricate and fascinating events spanning billions of years. It all begins in the early universe, shortly after the Big Bang, when the primordial soup of hydrogen and helium began to cool. Small density fluctuations in this otherwise uniform universe allowed gravity to exert its influence, pulling material together to form the first proto-galaxies and stars in what we call the cosmic web. In these early epochs, small clusters of gas and dark matter coalesced under gravity's pull to form primordial galaxies. These tiny galaxies acted as the seeds for larger structures over time. Through a series of mergers and accretions, these small entities combine to form larger galaxies. This hierarchical buildup is a key aspect of the lambda cold dark matter cosmological model, which describes how galaxies grow and evolve. Interactions and mergers not only increased a galaxy's mass, but also stirred up the gas within them, often triggering bursts of star formation, known as starbursts. The shape and structure of a galaxy can also change dramatically through these mergers. For instance, when spiral galaxies collide, they often create elliptical galaxies, as the chaotic interaction causes the orderly disk structures to dissipate into more rounded shapes. Some evidence supporting this can be found in galaxy clusters, where elliptical galaxies are more common, suggesting that they've undergone multiple merger events over time. Meanwhile, spiral galaxies like the Milky Way tend to reside in less densely populated regions, allowing them to maintain their spiral structures because they experience fewer disruptive collisions. Throughout this ongoing process of growth and interaction, individual galaxies also evolve through internal mechanisms. Spiral galaxies, for example, can cultivate new stars for billions of years, gradually transforming their interstellar gas into stars. Once the gas supply dwindles, star formation slows down, and the galaxy ages and changes in appearance, transitioning from a youthful blue, spiraled form to a more sedate, redder hue populated by older stars. Feedback from supernova explosions and activity from supermassive black holes at galaxy centers also play a crucial role in shaping a galaxy's evolution by regulating star formation and dispersing gas. Overall, the life of a galaxy is a dynamic narrative of continuous formation, growth, transformation, and sometimes dramatic interaction. From the silent, dark birthplaces of the early universe to the intricate and luminous structures we observe today, the evolutionary journeys of galaxies showcase the intricate interplay of cosmic forces that sculpt the universe. Dark matter and dark energy are enigmatic components of our universe that wield substantial influence over the structure and evolution of galaxies, despite their elusive nature. Though they constitute about 85% of the matter in the universe, dark matter does not emit, absorb, or reflect light, making it invisible to traditional observational methods. Similarly, dark energy, which accounts for about 70% of the total energy content of the universe, is equally mysterious and is thought to be responsible for the accelerated expansion of the cosmos. In the context of galaxy formation and structure, dark matter acts as the scaffolding upon which galaxies are built. During the early universe, regions of slightly higher dark matter density acted as gravitational wells, pulling in normal matter and leading to the formation of proto-galaxies. The presence of dark matter halos A spherical distribution of dark matter surrounding galaxies provides the necessary gravitational glue to hold galaxies together. Observations of galactic rotation curves, where the outer regions of galaxies rotate faster than expected, based solely on visible matter, provide strong evidence for the presence of these dark matter halos. Without dark matter, galaxies would have insufficient gravitational pull to keep their stars, gas, and dust from flinging outwards. Dark matter also influences galactic interactions and mergers. When galaxies collide, their dark matter halos can pass through each other with minimal interruption, as dark matter interacts primarily through gravity rather than electromagnetically. This behavior can enhance the rate of galactic mergers, thereby impacting the shapes and sizes of resultant galaxies. The largest structures in the universe, such as galaxy clusters, also owe their existence to the gravitational influence of dark matter, which binds hundreds or even thousands of galaxies together in these colossal assemblies. Dark energy, on the other hand, plays a somewhat different but equally consequential role. It is theorized to be responsible for the accelerated expansion of the universe, discovered through observations of distant supernovae and cosmic microwave background radiation. While this accelerated expansion may seem to exert a more global effect, it indirectly impacts galaxies. As the universe expands faster and faster, the gravitational pull between galaxies weakens, making future mergers and interactions less likely. Additionally, dark energy influences the large-scale structure of the universe, contributing to the cosmic web's distribution of galaxies and voids. Dark matter and dark energy are fundamental to understanding the cosmic architecture. Dark matter creates the framework that holds galaxies together, while dark energy drives the expansion dynamics of the universe. Together, these mysterious components orchestrate the intricate dance of galaxies, shaping the universe on both local and cosmic scales. The Andromeda Galaxy, also known as M31, holds a place of prime importance in the cosmic neighborhood of the Milky Way. Positioned about 2.5 million light-years away, it is the nearest spiral galaxy to our own, and one of the most massive members of the local group, which comprises around 54 galaxies, including the Milky Way. Andromeda's significance is underscored by several key factors, not least of which is its impending collision with the Milky Way, an event that will have profound implications for the structure and future of both galaxies. Andromeda is slightly larger than the Milky Way, containing over 1 trillion stars compared to our galaxy's estimated 200 to 400 billion. This mass helps Andromeda exert a significant gravitational influence within the local group. One of the most captivating aspects of the relationship between the Milky Way and Andromeda is their approaching collision, driven by mutual gravitational attraction. The two galaxies are converging at a rate of about 70 miles per second. This colossal event is expected to occur in approximately 4.5 billion years, and will likely result in the merging of the two galaxies into a single larger elliptical galaxy, often referred to as Milkometa or Milkdromeda. The impending collision, while dramatic, is not something to fear, as the vast distances between stars mean that direct stellar collisions will be exceedingly rare. Instead, the gravitational interactions will result in a stunning transformation. The spiral structures of both galaxies will be disrupted, and their central supermassive black holes may eventually merge, emitting gravitational waves detectable across the cosmos. Such galactic mergers are not uncommon in the universe, and are a vital process in the evolution of galaxies. Beyond its role in this future cosmic event, Andromeda also provides astronomers with a valuable comparative model for studying galaxy formation and evolution. Its relative proximity allows for detailed observations that help scientists understand star formation, galactic dynamics, and the life cycle of galaxies. The similarities and differences between Andromeda and the Milky Way offer insights into how environmental factors and internal processes can shape the destiny of spiral galaxies. The Andromeda Galaxy serves as a mirror and a partner to the Milky Way, highlighting the intricate and dynamic nature of galactic relationships. Its eventual merger with our galaxy stands as a testament to the ever-changing, interconnected web of the universe, illustrating that even on a cosmic scale, nothing remains static, a notion that fills our view of the future with both awe and anticipation. Galaxy collisions are cosmic events that significantly mold the structure and evolution of the universe. These dramatic encounters have far-reaching consequences, affecting not just the colliding galaxies themselves, but also the broader cosmic environment. When galaxies collide, their gravitational forces intricately interact, influencing the formation of stars, the growth of supermassive black holes, and the overall morphology of the resulting galactic structures. In the initial stages of a collision, galaxies do not simply crash into each other like solid objects. Instead, they interpenetrate, and their stars, gas, and dark matter interact through complex gravitational interactions. These forces can trigger bursts of star formation as gas clouds compress and ignite new stellar nurseries. This starburst phase is often observable in colliding galaxies, like the antennae galaxies, where dazzling displays of new stars highlight the regions of interaction. In some cases, these starbursts can produce tens to hundreds of new stars simultaneously, significantly influencing the luminosity and evolution of the merging galaxies. As the collision progresses, the original shapes of the galaxies become distorted, with tidal forces stretching and warping them into new forms. These interactions can lead to the formation of tidal tails, long streams of stars and gas ejected into intergalactic space, as seen in systems like the Mice galaxies. Over time, the gravitational dance continues, with the galaxies repeatedly passing through each other and coalescing their cores. These repeated interactions gradually dissipate the ordered rotational structures typical of spiral galaxies, often resulting in the creation of an elliptical galaxy. The supermassive black holes at the centers of each galaxy may merge, releasing gravitational waves and potentially powering quasars or active galactic nuclei that can outshine the combined light of all the stars in their host galaxies. Galaxy collisions also play a crucial role on larger cosmic scales. They drive the hierarchical model of structure formation, where small galaxies merge to form larger ones over billions of years. This process helps to explain the diverse array of galaxy types we observe today, from the elegant spirals to the more amorphous ellipticals. In the context of galaxy clusters, collisions among member galaxies can influence the distribution of dark matter, intergalactic gas, and the overall dynamics of the cluster. Moreover, the remnants of these collisions, both the newly formed galaxies and the extended ejecta of stars and gas, contribute to the enrichment of the intergalactic medium with heavy elements forged in the hearts of stars. This material can seed future generations of star formation across the universe, further perpetuating the cycle of cosmic evolution. Galaxy collisions are transformative events that reshape the cosmic landscape, driving star formation, altering galactic morphologies, and fostering the growth of supermassive black holes. They underscore the dynamic and evolving nature of the universe as galaxies continuously interact and evolve, creating a tapestry of ongoing cosmic creation and transformation. A black hole, often a subject of deep fascination and scientific wonder, is a region in space where the gravitational field is so strong that nothing, not even light, can escape from it. These cosmic phenomena are born from the death throes of massive stars, roughly 20 times the size of our Sun, that collapse under their own gravity after exhausting their nuclear fuel. The core is compressed to an extremely small size, where density and gravity become infinitely large per our current understanding, leading to what is termed a singularity. Around this singularity lies the event horizon, the point beyond which nothing can return once crossed, making black holes essentially invisible to direct observation. Detecting black holes, given their nature, may seem an insurmountable challenge. However, scientists employ several ingenious methods. One primary technique is observing the behavior of nearby stars and gas clouds. If a star is seen to orbit an unseen companion, astronomers can infer the presence of a black hole from the star's movement and the gravitational effects at play. Another vital method is through the detection of X-rays emitted by the accretion disk, the hot, glowing material spiraling into the black hole. This material heats up and emits high-energy radiation just before crossing the event horizon. Moreover, groundbreaking advancements in gravitational wave astronomy, particularly through observatories like LIGO and Virgo, have recently allowed us to detect the ripples in space-time caused by the collision and merger of black holes. Through these methods, the once invisible and mysterious black holes are becoming some of the most well-understood objects in the cosmos. The event horizon of a black hole stands as one of the defining and most mysterious aspects of these celestial phenomena. Essentially, the event horizon is the boundary surrounding a black hole beyond which nothing can escape. This escape includes particles, electromagnetic radiation such as light, and even information itself. The reason for this is rooted in the intense gravitational pull that characterizes black holes, a force so overpowering that once matter and radiation cross this threshold, they are inexorably drawn inwards toward the singularity, forever lost from the rest of the universe. To comprehend the event horizon's function, imagine space as a stretched fabric. As objects with mass warp this fabric, the distortion represents gravity. A black hole, with its immense mass concentrated into an infinitely small point, creates a warp so deep that it essentially creates a hole in this fabric. The event horizon, the concept, a neutron star, one of the densest forms of matter in the universe, emerges from the explosive aftermath of a supernova. Picture an atom's nucleus crammed into a sphere just about 12 miles in diameter, yet containing a mass 1.5 to 2 times that of our Sun. This is a neutron star, a stellar remnant left behind when a massive star, typically 8 to 20 times the mass of the Sun, exhausts its nuclear fuel and undergoes a gravitational collapse. The process begins as the star's core contracts under the force of gravity, while the outer layers are expelled in a dramatic explosion known as a supernova. The supernova's colossal blast sheds the outer material into space, but what happens at the core is a symphony of extreme physics. As the core collapses, protons and electrons are forced to combine into neutrons due to the intense gravitational pressure. This neutron-rich core, no longer able to compress any further, stabilizes into a neutron star. The matter inside is so dense that a sugar cube-sized amount of neutron star material would weigh about as much as all of humanity combined. Neutron stars also possess incredibly strong magnetic fields and enormous rotational speeds, often observable as pulsars, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. Neutron stars are fascinating endpoints in stellar evolution, but they also spark many further questions. These celestial objects serve as natural laboratories for studying physics under extreme conditions. For instance, the composition and state of matter inside a neutron star are subjects of vigorous scientific inquiry, intersecting fields ranging from quantum mechanics to general relativity. The study of these dense remnants also helps refine our understanding of fundamental forces and the behavior of matter at densities far exceeding what we encounter on Earth. Pulsars and magnetars are specialized types of neutron stars, each showcasing the incredible variety of behaviors and characteristics that these dense stellar remnants can exhibit. Pulsars, for instance, are neutron stars that emit beams of radiation from their magnetic poles. As these stars rotate, and assuming their magnetic poles are not aligned with their rotational axis, the emitted radiation sweeps across space like the focused beam of a lighthouse. If one of these beams happens to point toward Earth, we detect it as regular pulses of radiation, hence the name pulsar. These pulses can occur at incredibly regular intervals, ranging from milliseconds to seconds, making pulsars some of the most precise natural clocks in the universe. The phenomena are so stable that astronomers even use them to test the fundamental laws of physics, such as general relativity. Magnetars, on the other hand, represent an extreme subset of neutron stars, characterized by their exceptionally strong magnetic fields, thousands of times stronger than those found in typical neutron stars, or even pulsars. These magnetic fields can be 1 quadrillion times stronger than Earth's magnetic field. Magnetars often also rotate relatively slowly compared to pulsars, with rotation periods ranging from a few seconds to several minutes. These potent magnetic fields lead to dramatic surface activity and violent outbursts, manifesting as intense bursts of X-rays and gamma rays. Such bursts can affect the star's crust, which is composed of ultra-dense neutron-rich matter, leading to starquakes and further bursts of high-energy emissions. Thus, pulsars and magnetars highlight the diversity within the neutron star family. While pulsars, with their rhythmic light pulses, help us explore the cosmos with precise timing, magnetars challenge our understanding of magnetic fields and high-energy astrophysics through their powerful emissions. Both phenomena offer unique windows into the extreme environments and fundamental physics at play in these dense post-supernova remnants, enriching our knowledge of the universe's most exotic objects. Among the myriad of black holes and neutron stars discovered, a few have garnered particular renown due to their unique properties, historical importance, or the groundbreaking science they facilitated. One of the most famous black holes is Cygnus X1, located in the constellation Cygnus, about 6,000 light-years from Earth. Discovered in the early 1970s, Cygnus X1 was one of the first strong candidates for a black hole. This binary system includes a blue supergiant star and its compact companion, the black hole, which exhibits powerful X-ray emissions as it accretes matter from the supergiant. The discovery of Cygnus X1 played a pivotal role in solidifying the concept of black holes within astrophysics, proving their existence beyond theoretical constructs. In the world of neutron stars, the Crab pulsar is iconic. Located at the heart of the Crab Nebula, the Crab pulsar is the remnant of a supernova explosion recorded by Chinese astronomers in 1054 AD. This pulsar rotates 30 times per second, emitting pulses of radiation across various wavelengths, including radio waves, optical light, X-rays, and gamma rays. The Crab pulsar is intensely studied because it offers a wealth of information about pulsar wind nebula, magnetic fields, and the mechanics of supernova remnants. The synchronization of observations across different electromagnetic spectrum bands makes the Crab pulsar a cornerstone in multi-wavelength astronomy. Another notable black hole is Sagittarius A, the supermassive black hole at the center of our Milky Way galaxy. Invisible to optical telescopes, its presence is inferred through the rapid orbits of nearby stars, which circle an unseen massive object with immense gravitational influence. Through techniques like radio and infrared observations, astronomers can map these stellar orbits and confirm the astounding mass of Sagittarius A, approximately 4 million times that of the Sun. The discovery and study of Sagittarius A have provided invaluable insights into the nature of supermassive black holes and their role in galaxy formation and evolution. For neutron stars, PSR B199+21 holds historical significance as the first pulsar ever discovered. Found by Jocelyn Bell and Anthony Hewish in 1967, its periodic radio pulses initially led to speculation about extraterrestrial intelligence before it was identified as a rapidly rotating neutron star emitting beams of radio waves. This discovery opened a new era for observational astrophysics, revealing new ways to study the extreme physics governing neutron stars. These famous black holes and neutron stars are not merely objects of cosmic curiosity. They are monumental in advancing our understanding of stellar evolution, gravitational theory, and the extreme states of matter, continually pushing the boundaries of what's known in modern astrophysics. The Big Bang Theory is the prevailing cosmological model explaining the origin of the universe. According to this theory, the universe began approximately 13.8 billion years ago from an extremely hot, dense state and has been expanding ever since. The notion of the Big Bang should not be confused with an explosion in the conventional sense. Rather, it was an event that marked the beginning of space-time and all the matter and energy that currently exists. The term Big Bang, initially coined somewhat pejoratively by British astronomer Fred Hoyle, has since become the widely accepted designation for this cosmological model. The Big Bang Theory finds strong support from multiple lines of empirical evidence. One of the most compelling pieces comes from the observation of the cosmic microwave background radiation, first detected accidentally by Arno Penzias and Robert Wilson in 1965. The cosmic microwave background is a faint glow that fills the universe and is considered the afterglow of the Big Bang itself, providing a snapshot of the infant universe when it was just 380,000 years old. This radiation is remarkably uniform, with tiny fluctuations that correspond to the seeds of all current cosmic structure, galaxies, stars, and planets. Another line of evidence is the redshift of galaxies, first described by Edwin Hubble. Hubble observed that galaxies appear to be moving away from us, with their light shifted towards the red end of the spectrum, indicating that space itself is expanding. This observation aligns with the predictions of general relativity, which Albert Einstein formulated earlier in the 20th century. When run backward, this expansion implies that the universe was once much more condensed. Furthermore, the abundance of light elements, such as hydrogen, helium, and traces of lithium, as predicted by Big Bang nucleosynthesis, also supports this theory. These elements were formed during the first few minutes of the universe, when temperatures and pressures were so high that nuclear reactions could occur, creating these primordial elements in quantities that match what we observe today. The Big Bang Theory provides a comprehensive framework for understanding the universe's origin and its subsequent evolution. It not only accounts for current observations, but also continuously guides new discoveries, enhancing our grasp of the cosmos as it evolves over billions of years. Determining the age and size of the universe relies on a blend of observational astronomy, theoretical physics, and advanced mathematical modeling. To measure its age, one of the key methods involves studying the cosmic microwave background radiation, which is the oldest light in the universe. This relic radiation from the Big Bang, first detected by Arno Penzias and Robert Wilson in 1965, provides a direct window into the early universe. By analyzing the tiny fluctuations in the cosmic microwave background, scientists can infer crucial cosmological parameters, such as the rate of expansion of the universe, known as the Hubble constant. Microwave observatories like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have provided precise measurements of these fluctuations, leading to the most accurate estimates of the universe's age. Current calculations suggest that the universe is approximately 13.8 billion years old. Another approach involves studying the oldest known star clusters, such as globular clusters. These densely packed groups of ancient stars provide a lower bound on the age of the universe. By determining the age of the oldest stars within these clusters, which can be done through understanding stellar evolution and nucleosynthesis, astronomers validate and refine the age derived from the cosmic microwave background data. These stars' ages are consistent with the universe being several billion years old, corroborating the results derived from cosmic background studies. Measuring the size of the universe, particularly the observable universe, is intertwined with understanding its expansion. Edwin Hubble's observation that galaxies are receding from us, with more distant galaxies moving faster, paved the way for estimating cosmic scale. The Hubble constant, which quantifies this expansion rate, is critical for calculating distances. Modern measurements using Type 1a supernovae as standard candles, a method where the intrinsic brightness of these exploding stars is well understood, help refine the value of the Hubble constant. Alongside baryon acoustic oscillations, which are periodic fluctuations in the density of visible baryonic matter, provide another standard ruler for cosmological distances. Combining the Hubble constant with the current age of the universe allows scientists to estimate the size of the observable universe. Since light travels at a finite speed, looking out into space is also looking back in time. Hence, the observable universe is a sphere around us with a radius of about 93 billion light-years. This is far larger than the age of the universe multiplied by the speed of light due to the continuous expansion of space itself. Through these integrated methods, examining the cosmic microwave background, star clusters, supernovae, and cosmic expansion, scientists piece together a picture of the universe's vast age and size, offering profound insights into the cosmos's observable boundaries and its dramatic history. Cosmic background radiation, more formally known as the cosmic microwave background, is a pervasive afterglow of the Big Bang, presenting itself as a faint microwave radiation that fills the entire universe. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, the cosmic microwave background represents the residual heat left over from the initial explosion that created the universe. This radiation dates back to approximately 380,000 years after the Big Bang, a time when the universe had cooled sufficiently to allow protons and electrons to combine into neutral hydrogen atoms, making the universe transparent and allowing light to travel freely for the first time. The cosmic microwave background is essentially a snapshot of the universe at that infant stage. The importance of cosmic background radiation to cosmology cannot be overstated. First and foremost, it provides strong empirical support for the Big Bang theory. The near-perfect uniformity of the cosmic microwave background, with minute temperature variations of about 1 part in 100,000, fits precisely with predictions from the Big Bang model concerning the early universe's homogeneous and isotropic nature. These minute fluctuations are significant. They represent the seeds of all current structure in the universe, galaxies, stars, and planets, indicating regions of slightly varying densities that grew over billions of years into the cosmic structures we observe today. Detailed measurements of the cosmic microwave background, particularly from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have provided a treasure trove of cosmological data. These observations allow scientists to refine the values of several critical cosmological parameters, such as the Hubble constant, the rate of expansion of the universe, the density of ordinary matter, dark matter, and dark energy. By meticulously analyzing the cosmic microwave background, scientists can also determine the universe's age to a high degree of precision, which is currently estimated at around 13.8 billion years. Moreover, the cosmic microwave background has revealed evidence of cosmic inflation, a rapid expansion of the universe immediately following the Big Bang. Information encoded in the temperature and polarization patterns of the cosmic microwave background supports this inflationary model, providing insights into the universe's first fractions of a second. These studies open up avenues for understanding fundamental physics at energies far beyond those accessible through particle accelerators on Earth. Cosmic background radiation serves as a vital cosmic relic, a faint whisper of the universe's explosive birth and its subsequent evolution. It provides us with a detailed map of the early universe, guiding our comprehension of the cosmos from its inception to its current vast, structured form, and continues to be an essential source of data for ongoing and future astrophysical research. Scientists study the expansion of the universe primarily through the observation of distant galaxies and the light they emit. One of the foundational methods relies on the redshift of light, a phenomenon first systematically studied by Edwin Hubble in the 1920s. Redshift occurs because as galaxies move away from us due to the expansion of space, the light traveling from these galaxies gets stretched, shifting it toward the red end of the electromagnetic spectrum. This shift can be quantified using spectroscopic techniques, where the absorption or emission lines of elements observed in a galaxy's spectrum are compared to their known laboratory wavelengths. The amount of redshift directly correlates with the galaxy's velocity and distance, providing a measure of how fast they are receding and consequently a measure of the universe's expansion rate. An essential tool in this process is the Hubble constant, symbolized as h0, which quantifies the rate of expansion of the universe. This constant is derived from Hubble's law, which states that the velocity of a galaxy, v, is directly proportional to its distance, d, from us, with h0 being the proportionality constant, v h0 checks d. Measuring the Hubble constant requires precise distance measurements to galaxies, which astronomers achieve through several methods. One key approach involves using standard candles, such as Type 1a supernovae. These supernovae have a consistent intrinsic brightness, allowing their distance to be calculated by comparing their known luminosity to their observed brightness. By mapping the distances against the redshifts of these supernovae, scientists provide a more accurate value for the Hubble constant, thereby refining our understanding of the rate of expansion. The study of cosmic background radiation, or CMB, provides another critical avenue for understanding expansion. The cosmic microwave background is the afterglow of the Big Bang, uniform in all directions, but with tiny temperature fluctuations that offer insight into the early universe's conditions. Space missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured these fluctuations with high precision. Analysis of the cosmic microwave background helps determine several cosmic parameters, including the universe's geometry, and the rate of its expansion over time. These observations reinforce the measurements derived from distant galaxies and supernovae, giving a cohesive picture of the universe's expansion history. Finally, scientists also use baryon acoustic oscillations as a standard ruler for cosmic distances. Baryon acoustic oscillations refers to regular periodic fluctuations in the density of visible matter due to sound waves traveling through the early universe. These sound waves have left their imprint on the large-scale distribution of galaxies. By measuring the scale of baryon acoustic oscillations in the distribution of galaxies, astronomers can further refine the distance measures necessary to calculate the universe's expansion rate. The expansion of the universe is studied through a multifaceted approach, combining observations of distant galaxies, supernovae, the cosmic background radiation, and large-scale cosmic structures. These methodologies converge to provide a detailed and evolving picture of how space itself has been stretching and growing ever since the Big Bang, guiding our understanding of the dynamic and expanding universe we inhabit. The ultimate fate of the universe is one of cosmology's most profound questions, and several leading theories propose different scenarios based on our understanding of current cosmological parameters, particularly the nature of dark energy, dark matter, and the universe's overall geometry and expansion rate. One of the primary theories is the Big Freeze, also known as heat death. This scenario depends heavily on the concept of dark energy, which appears to be driving the accelerated expansion of the universe. Should this acceleration continue indefinitely, galaxies will drift further apart, reducing interactions such as galaxy mergers and star formation. Over billions to trillions of years, stars will exhaust their nuclear fuel, and the formation of new stars will cease, leaving behind a universe increasingly dominated by cold, dark remnants like white dwarfs, neutron stars, and black holes. Eventually, even black holes might evaporate through a process called Hawking radiation, leading to a final state where the universe is a sparse, cold expanse filled with low-energy photons and elementary particles. Another theory is the Big Crunch. In this scenario, the expansion of the universe will eventually halt and reverse if the gravitational attraction of the universe's matter, including dark matter, overcomes the repulsive force of dark energy. This reversal would cause galaxies to converge back towards each other, leading to increasing density and temperature throughout the universe. Ultimately, the universe could collapse back into a singular state, mirroring conditions similar to those at the Big Bang, possibly setting the stage for a cyclic model of perpetual expansion and contraction. A related theory to the Big Crunch is the Big Bounce. Here, the universe undergoes repeated cycles of expansion and contraction. After contracting into an extremely dense state, similar to a Big Crunch, quantum gravitational effects might cause a rebound, leading to another Big Bang and a new cycle of expansion. This theory attempts to merge principles of quantum mechanics with general relativity to explain the universe's behavior at extreme densities. A more recently discussed fate is the Big Rip. This scenario stems from certain models of dark energy, particularly those involving a form of dark energy called phantom energy, which increases in strength over time. If dark energy grows stronger than all other forces, it could eventually rip apart galaxies, stars, planets, and even atomic nuclei, leading to a universe where space itself is torn apart. The Big Rip predicts a dramatic end, where the force driving the expansion overwhelms every binding force at every scale. Lastly, there is the heat death scenario, different from the Big Freeze mainly in how it emphasizes achieving a state of thermodynamic equilibrium. In this context, the universe reaches maximum entropy, where all energy is uniformly distributed and no difference in temperature exists to drive any form of work or processes. This will be the ultimate state of inactivity, a uniform, featureless expanse where the thermodynamic arrow of time has essentially run its course. These theories are continually refined and tested as our understanding of dark energy, dark matter, and other cosmological factors improves. Current and future observations, such as those from the James Webb Space Telescope or gravitational wave detectors, will be crucial in further constraining these models, helping to illuminate the profound question of the universe's ultimate destiny. The search for and study of dark matter and dark energy are among the most exciting and challenging pursuits in modern astronomy and physics. Both components appear to play fundamental roles in the cosmos, yet remain elusive because they do not interact with light in ways that make them easily observable. Scientists employ a variety of methods to infer their presence and study their properties. Dark matter is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the key pieces of evidence comes from the rotational curves of galaxies. When scientists observe the rotation speeds of stars within galaxies, they find that the outer stars rotate much faster than can be explained by the visible mass alone. This discrepancy strongly suggests the presence of an unseen mass attributed to dark matter. Additionally, the gravitational lensing effect, where light from distant objects is bent around massive clusters of galaxies, provides another line of evidence. The degree of bending exceeds what would be expected from visible matter alone, pointing to substantial amounts of dark matter. Efforts to detect dark matter directly are ongoing and involve highly sensitive detectors placed deep underground to shield them from cosmic rays and other background radiation. These experiments, like the cryogenic dark matter search and the xenon dark matter experiment, aim to detect rare interactions between dark matter particles and normal matter. Other avenues include accelerator experiments, such as those conducted at the Large Hadron Collider, hoping to produce dark matter particles in high-energy collisions. Dark energy, on the other hand, is believed to be the force driving the accelerated expansion of the universe. Its presence was first inferred from observations of Type 1a supernovae in the 1990s, revealing that distant supernovae appeared dimmer than expected, suggesting that the universe's expansion rate is increasing. Dark energy constitutes about 70% of the universe's total energy content, yet its exact nature remains a profound mystery. The study of dark energy involves several approaches. One primary method is the observation of large-scale structures in the universe, such as galaxy clusters and voids. Surveys like the Sloan Digital Sky Survey and the Dark Energy Survey map the distribution of these structures to track how they evolve over time. Another crucial observation comes from the cosmic microwave background radiation. Instruments like the Planck satellite provide detailed measurements of the cosmic microwave background, allowing scientists to infer the universe's geometry and expansion history. The behavior of baryon acoustic oscillations, sound waves from the early universe imprinted in the distribution of galaxies, also offers insights into the expansion rate influenced by dark energy. Future missions and projects aim to further our understanding of both dark matter and dark energy. The upcoming Euclid satellite and the James Webb Space Telescope will provide unprecedented data, and ground-based observatories like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will offer comprehensive sky surveys. These efforts are complemented by theoretical work aiming to better integrate dark matter and dark energy into the framework of particle physics and general relativity. The quest to unveil dark matter and dark energy involves a multifaceted strategy combining observational evidence from telescopes, experimental searches in particle physics, and theoretical developments. While these components remain enigmatic, their study continues to push the boundaries of our understanding, enriching our conception of the universe's composition and its ultimate fate. Exoplanets, or extrasolar planets, are planets that orbit stars outside our solar system. These celestial bodies vary widely in size, composition, and orbital characteristics, offering a fascinating glimpse into the diversity of planetary systems. Since the first confirmed detection in 1992 of exoplanets orbiting the pulsar PSR B127+12, the field has expanded dramatically, with thousands of exoplanets now cataloged thanks to advanced detection methods and technologies. One of the most effective techniques for discovering exoplanets is the transit method. This method involves monitoring the brightness of a star over time. If a planet passes directly between its star and the observer, it causes a temporary dimming of the star's light, a transit. By measuring the depth, duration, and periodicity of these transits, astronomers can infer the planet's size, its orbital period, and even some atmospheric properties if the star's light filters through the planet's atmosphere. NASA's Kepler Space Telescope revolutionized this method, discovering over 2,000 confirmed exoplanets by observing a fixed field of stars and detecting the tiny dips in brightness caused by planetary transits. Another well-established method is radial velocity, or the Doppler method. This technique measures the wobble in a star's motion caused by the gravitational influence of an orbiting planet. As the star moves towards and away from us, its light shows a slight redshift and blue shift due to the Doppler effect. By analyzing these shifts with high-precision spectrometers, scientists can determine the planet's mass and orbit. Ground-based telescopes, such as those using the HARP spectrograph in Chile, have been instrumental in detecting exoplanets through this method. Gravitational microlensing offers another intriguing avenue for discovery. It relies on the gravitational field of a massive object, like a star, which bends the light of a background star. If a planet orbits the intermediary star, it can create a distinct temporary brightening in the background star's light, a microlensing event. This method is particularly effective for finding planets at greater distances from their stars, even in planetary systems located several thousand light-years away, although it does require precise alignments and is often used in conjunction with other methods. Direct imaging, though challenging, is a growing field. This method involves capturing pictures of exoplanets by blocking out the star's bright light, often using a coronagraph or a starshade. Advances in technology and adaptive optics have made it possible to directly image larger exoplanets, especially those orbiting relatively far from their host stars. The James Webb Space Telescope is expected to push the boundaries of direct imaging, allowing us to study exoplanet atmospheres in greater detail. Last but not least, astrometry measures the precise changes in a star's position in the sky due to the gravitational effect of an orbiting planet. Though less commonly used due to the necessity of extremely accurate measurements, astrometry can be highly effective for detecting planets with longer orbital periods. These discovery methods, employed individually or in complementary combinations, enable scientists to characterize exoplanets' masses, radii, orbital distances, and atmospheric compositions. Each new discovery adds to our understanding of planet formation and the potential for habitability, bringing us closer to answering whether life exists beyond our solar system. With missions like TESS transiting Exoplanet Survey Satellite, the James Webb Space Telescope, and upcoming projects like ESA's Plato, Planetary Transits and Oscillations of Stars, The search for and study of exoplanets continue to be an exhilarating frontier in modern astronomy. Scientists use several sophisticated methods to detect exoplanets, each with its own strengths and limitations. These techniques exploit the effects that planets have on their host stars and the light these stars emit. One of the most successful and widely used methods is the transit method. This involves observing the light from a star and looking for periodic dips in brightness, which occur when a planet passes in front of the star, briefly blocking a portion of its light. This transit causes measurable reductions in brightness that can provide information about the planet's size and orbital period. NASA's Kepler Space Telescope has identified over 2,000 confirmed exoplanets using this method. By further analyzing how the star's light changes as it filters through the planet's atmosphere during transit, scientists can infer the composition of the planet's atmosphere, detecting gases like hydrogen, helium, and water vapor. Another cornerstone technique is the radial velocity method, also known as the Doppler method. As a planet orbits a star, the gravitational pull between them causes the star to move in a small orbit, resulting in shifts in the star's spectral lines due to the Doppler effect. When the star moves toward Earth, its light is slightly blue shifted. When it moves away, it is red shifted. High-precision spectrometers, like those employed in the HARPS, High Accuracy Radial Velocity Planet Searcher instrument at the La Silla Observatory in Chile, can detect these subtle changes in the star's velocity. This method provides information about the planet's minimum mass and orbital eccentricity. Gravitational microlensing is a method that relies on the gravitational field of a star to magnify the light from a more distant background star when they align closely. If the foreground star has a planet, it can cause an additional noticeable blip in the light profile, a microlensing event. This technique is especially adept at detecting planets far from their host stars, including those in systems thousands of light years away, which might be missed by other methods. Direct imaging involves capturing visual or infrared images of planets by blocking out the light from the host star, usually with a coronagraph or a starshade, to reduce the star's glare. Although challenging due to the faintness of planets compared to their stars, recent advancements in adaptive optics and the use of space telescopes have made this method increasingly viable. Direct imaging allows scientists to study the atmospheres and even the weather patterns of exoplanets by analyzing the emitted or reflected light. Lastly, astrometry measures the precise movements of stars in the sky, looking for the tiny wobbles caused by orbiting planets. This method requires extremely high precision because the positional changes are minuscule. While it's less commonly used due to technological challenges, it can be effective for detecting massive planets in wide orbits. These techniques often complement each other. For example, initial detections made by the transit or radial velocity methods can be followed up with direct imaging or atmospheric analysis during transits to gather more comprehensive data. Each method brings us closer to understanding the vast diversity of planetary systems in our galaxy and the potential for life beyond our solar system. With missions like TESS, Transiting Exoplanet Survey Satellite, the JWST, James Webb Space Telescope, and ESA's Plato, Planetary Transits and Oscillations of Stars, the detection and study of exoplanets are becoming ever more precise and insightful, opening new frontiers in the search for extraterrestrial life. An exoplanet's potential habitability hinges on several key factors, primarily related to its capacity to support liquid water, which is considered essential for life as we know it. The most critical criteria include the exoplanet's location within its star's habitable zone, its size and composition, atmospheric conditions, and the stability and activity of its host star. The habitable zone, often termed the Goldilocks zone, is the region around a star where the temperature is just right for liquid water to exist on a planet's surface, not too hot and not too cold. This zone's distance varies depending on the star's type and luminosity. For instance, around a sun-like star, the habitable zone might stretch from about 0.95 to 1.37 astronomical units from the star, with 1 astronomical unit being the distance from Earth to the Sun. For a smaller, cooler star like an M dwarf, the habitable zone would be much closer in. Discovering an exoplanet within this zone is the first significant step toward assessing its habitability. Size and composition are also crucial. Ideally, a potentially habitable exoplanet should be about Earth-sized, meaning it has a radius and mass not drastically different from our own planet. This implies it is more likely to have a rocky surface, as opposed to being a gas giant. Planets that are too large may attract thick hydrogen-helium atmospheres, making them more like Neptune or Jupiter than Earth. Alternatively, planets significantly smaller than Earth may struggle to retain a substantial atmosphere, which is vital for maintaining liquid water and protecting life forms from harmful stellar radiation. The planet's atmosphere plays a pivotal role in regulating surface temperature through the greenhouse effect, distributing heat, and providing essential gases for potential biological processes. A planet with an atmosphere thick enough to retain heat, but not so thick as to create a runaway greenhouse effect like on Venus, is considered more habitable. The presence of water vapor, carbon dioxide, and traces of other gases like methane and oxygen can be promising signs. Advanced telescopes and spectrometers can analyze the composition of exoplanet atmospheres during transits or through direct imaging, offering hints about their potential to support life. The stability and activity of the host star are vital factors as well. Stars that are too volatile, such as those emitting frequent intense solar flares, can strip away atmospheres and bathe their planets in harmful radiation, making conditions challenging for life. Therefore, stars with relatively stable output and longer lifespans, like our Sun, are more conducive to habitability. Interestingly, M dwarfs or red dwarfs, despite being cooler and dimmer, have incredibly long lifespans, and their habitable zones are close in. However, their propensity for flares poses a potential risk to habitability. Other considerations include the planet's axial tilt and orbital eccentricity, which affect seasonal variations and overall climate stability, as well as the presence of a magnetic field, which can protect the atmosphere from stellar winds and cosmic radiation. Recent missions have identified several intriguing candidates, such as Proxima Centauri b, which orbits within the habitable zone of the closest star to the Sun, and the TRAPPIST-1 system, which hosts multiple Earth-sized planets within its habitable zone. Upcoming missions and telescopes like the James Webb Space Telescope and the Extremely Large Telescope promise to provide more detailed insights into these worlds, analyzing their atmospheres and searching for potential biosignatures. The search for potentially habitable exoplanets involves a complex interplay of factors, each contributing to the delicate balance required to sustain life as we understand it, advancing our quest to find another Earth among the stars. Imagine peering into the skies of distant worlds, hundreds of light years away, as if through a celestial magnifying glass. That's precisely what astronomers do to study the atmospheres of exoplanets, those planets that orbit stars beyond our Sun. One of the primary methods involves a technique called transit spectroscopy. When an exoplanet passes in front of its host star, some of the starlight filters through the planet's atmosphere. By capturing this light with powerful telescopes, scientists can analyze it to detect the presence of various molecules. Tiny signatures in the light spectrum, known as absorption lines, reveal the chemical composition of the exoplanet's atmosphere. These fingerprints can indicate molecules like water vapor, carbon dioxide, methane, or even more exotic substances, painting a vivid picture of what these strange and distant environments might be like. But the quest to understand these alien atmospheres doesn't stop there. Another vital method is direct imaging, though it is significantly more challenging. When astronomers manage to capture a direct image of an exoplanet, they can sometimes study its reflected light to glean information about the atmosphere. Instruments like the James Webb Space Telescope and other advanced observatories utilize adaptive optics and coronagraphs to block out the overwhelming glare of the parent star, allowing the fainter light from the exoplanet to come through. By analyzing this light, researchers can determine the temperature, weather patterns, and even the potential for habitability. This sophisticated approach, combined with theoretical models, allows scientists to extrapolate not just the atmospheric makeup, but also the possible climate and conditions, revealing whether some of these distant worlds might support life as we know it, or present environments beyond our wildest imaginings. In the boundless cosmic ocean where billions of stars hold sway, a select few exoplanets have captured the imaginations of scientists searching for extraterrestrial life. One of the prime candidates is Proxima Centauri b, an Earth-sized planet orbiting within the habitable zone of Proxima Centauri, the closest star to our Sun at a mere 4.24 light-years away. Discovered in 2016, Proxima Centauri b's location permits the possibility of liquid water on its surface, which is crucial for life as we know it. Ongoing observations aim to understand its atmosphere, surface conditions, and potential for sustaining life, making it a tantalizing target in the quest for otherworldly neighbors. Another set of intriguing worlds lies within the TRAPPIST-1 system, where 7 Earth-sized exoplanets orbit an ultra-cool dwarf star just 39 light-years away. Remarkably, 3 of these planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, exist within the star's habitable zone. The orbits of these planets are so tight that a year on one of them could last only a few days by our earthly standards. Spectroscopic studies of the TRAPPIST-1 planets have already begun to provide insights into their atmospheric composition. These worlds' size, density, and distance from their host star suggest they might host liquid water and potentially life. The TRAPPIST-1 system thus represents a fascinating laboratory for studying exoplanetary atmospheres and assessing life's potential beyond Earth, making it a cornerstone in the search for the extraordinary in the ordinary expanse of our galaxy. The Drake equation is a remarkable intellectual tool devised to estimate the number of active, communicative extraterrestrial civilizations within our Milky Way galaxy. Crafted by astrophysicist Frank Drake in 1961, the equation offers a way to quantify what might otherwise seem an incomprehensible question. It breaks down the immense complexity of the search for extraterrestrial intelligence into a series of manageable factors. These factors include the rate of star formation in the galaxy, the fraction of those stars that host planetary systems, and the number of planets per solar system that might be hospitable to life. From there, it delves further into the likelihood of life arising on such planets, the odds that such life forms develop intelligence, and finally, the probability that these intelligent beings develop technologies that allow them to communicate across interstellar distances. Each variable in the Drake equation requires a mix of observational data, theoretical understanding, and a bit of educated guesswork, as some factors remain largely speculative. For instance, while we have considerable data on the rate of star formation and the prevalence of exoplanets thanks to missions like Kepler, estimates for the emergence of life the development of intelligence, and the lifespan of technological civilizations involve more uncertainty. Despite these uncertainties, the true power of the Drake equation lies in its framework, which allows scientists to systematically approach the search for extraterrestrial intelligence, SET. By updating the equation's factors with new discoveries, scientists can continuously refine our estimate of the number of civilizations, shining light on the profound question, are we alone in the galaxy? Through collaborative international efforts and technological advancements, the quest driven by the Drake equation persists, ever adaptive to the expanding horizons of our astronomical knowledge. The Apollo missions stand as monumental milestones in the annals of human achievement, with Apollo 11's historic landing on the Moon in 1969 forever etched into the collective memory of humanity. This astonishing feat saw astronauts Neil Armstrong and Buzz Aldrin become the first humans to set foot on another celestial body, a testament to the boundless ingenuity and perseverance of those involved. Armstrong's famous words, "That's one small step for man, one giant leap for mankind," echoed the significance of this unprecedented venture. The Apollo program was not limited to just planting a flag and leaving footprints. It brought back over 840 pounds of lunar rocks, soil, and core samples, which fundamentally transformed our understanding of the Moon's composition and geological history. Yet, the Apollo missions were about much more than just reaching and returning from the Moon. They epitomize the power of scientific exploration and technological advancement. The Apollo missions led to significant development in many areas, from computing to engineering. The Saturn V rocket, the most powerful rocket ever built, successfully propelled astronauts beyond Earth's gravity. Scientific experiments left on the lunar surface, such as seismometers and retroreflectors, provided valuable data about the Moon's internal structure and its interaction with Earth. Apollo 12 through Apollo 17 expanded on the initial achievement with extended lunar surface explorations, the deployment of scientific instruments, and the use of the Lunar Roving Vehicle, which allowed astronauts to travel farther from their landing sites. The combined achievements of the Apollo missions laid the groundwork for contemporary space exploration and provided enduring inspiration, reflecting the remarkable possibilities when human ambition and scientific inquiry intertwine. The International Space Station represents a pinnacle of global collaboration and scientific inquiry. Orbiting Earth approximately 250 miles above its surface, since its inception in 1998, the International Space Station has served as an invaluable platform for conducting experiments that would be impossible under Earth's gravity. Through long-duration missions, scientists have been able to study the effects of microgravity on the human body, yielding crucial insights for future astronauts who may embark on extended journeys to Mars and beyond. Research on muscle atrophy, bone density loss, and fluid shifts within the body has led to the development of countermeasures and a better understanding of how space travel impacts human physiology, which is vital for long-term survival in outer space. Beyond the realm of biology, the International Space Station has also become a laboratory for a diverse range of scientific disciplines. Studies in physics, for instance, have benefited from the microgravity environment to explore phenomena like fluid dynamics and combustion in ways that are not possible on Earth. The International Space Station has also served as a launch pad for astronomical observations and Earth sciences. Instruments aboard the station have monitored cosmic rays, scanned the universe for dark matter, and observed Earth's atmosphere, oceans, and land surfaces, helping to track climate change and natural disasters. Moreover, international collaborations on the International Space Station have fostered technological advancements and diplomatic ties among participating countries, demonstrating the unity that space exploration can engender. By continuously leveraging its unique position in low Earth orbit, the International Space Station remains a beacon of scientific progress and a crucial stepping stone for the future exploration of deeper space. The Mars rovers Curiosity and Perseverance are at the forefront of humanity's quest to unravel the mysteries of the Red Planet. Launched by NASA, these advanced robotic explorers are tasked with delving into the planet's history and assessing its potential to have hosted life. Curiosity, which landed in Gale Crater in 2012, has a prime objective to investigate whether Mars ever had environmental conditions that could support microbial life. Equipped with a suite of scientific instruments, Curiosity has been analyzing rock and soil samples for organic compounds and other chemical indicators of habitability. The rover's discovery of ancient riverbeds and lakebeds, alongside the detection of complex organic molecules, has already provided compelling evidence that Mars could have been hospitable to life billions of years ago. Perseverance, which touched down in Jezero Crater in 2021, builds on Curiosity's legacy, but dives even deeper into the search for signs of past life. One of its primary missions is to collect and cache soil and rock samples that could potentially contain biosignatures, traces left by ancient microbial life. These samples are intended to be returned to Earth in a future mission for detailed laboratory analysis. Perseverance is also equipped with groundbreaking technology to study Mars's geology and climate, and it actively scouts for potential landing sites for human missions. Additionally, Perseverance has brought along Ingenuity, a small helicopter that has already proven powered flight on another planet is possible, opening up new avenues for aerial exploration. Through these multifaceted endeavors, both rovers are laying the groundwork not only for future scientific discovery, but also for the eventual human exploration of Mars, transforming our understanding of the planet, one groundbreaking discovery at a time. Voyager and New Horizons represent marvels of human ingenuity, each embarking on extraordinary journeys to explore the outer reaches of our solar system and beyond. The twin Voyager spacecraft, launched in 1977, were designed initially for a grand tour of the outer planets. Voyager 1 and Voyager 2 delivered unprecedented close-up images and data from Jupiter, Saturn, Uranus, and Neptune, dramatically expanding our understanding of these distant worlds. Equipped with a suite of scientific instruments including cameras, magnetometers, and plasma detectors, the Voyagers revealed details such as the rings of Jupiter, the complex atmospheres of Saturn and Neptune, and the active volcanism on Io, one of Jupiter's moons. As if these missions weren't ambitious enough, both Voyager spacecraft have since traveled into interstellar space, becoming our first human-made objects to leave the heliosphere, the bubble of solar wind surrounding our solar system. Their instruments continue to send back valuable data about the interstellar medium, providing insights into the environment that lies beyond the influence of our sun, and in turn, enhancing our understanding of our place in the galaxy. New Horizons, launched in 2006, epitomized a singular mission to explore Pluto and the Kuiper Belt. After a journey of nearly a decade, New Horizons made its closest approach to Pluto in 2015, capturing detailed images and data that transformed our view of this distant dwarf planet. The mission unveiled Pluto's complex geology, including towering mountains and vast plains of nitrogen ice, challenging previous assumptions about what such a distant and cold world could look like. Riding on the success of its Pluto flyby, New Horizons was directed to a secondary target, a Kuiper Belt object known as Arakoth, which it encountered in 2019. This flyby provided a glimpse into the building blocks of our solar system, revealing a primordial world with a surprisingly smooth and unblemished surface. Both the Voyager and New Horizons missions highlight humanity's insatiable curiosity and quest for knowledge. They not only provided a treasure trove of scientific data, but also served as beacons to the boundless frontiers that await us in the cosmos, each milestone pushing the boundary of what we can achieve and discover in space exploration. As humanity sets its sights on returning to the moon and venturing to Mars, the objectives of these future missions are both ambitious and multifaceted, encompassing scientific inquiry, technological innovation, and the foundation for potential human colonization. For lunar exploration, NASA's Artemis program aims to land the first woman and the next man on the moon by the mid-2020s. A key objective is to establish a sustainable human presence on the moon by the end of the decade. This includes the construction of the Lunar Gateway, a space station in orbit around the moon that will serve as a hub for future missions. By studying the lunar surface and its resources, like water ice potentially buried in the permanently shadowed craters of the poles, scientists hope to learn how to use these resources for life support and fuel, making lunar habitation more feasible. On the scientific front, lunar missions will focus on understanding the moon's geology, origin, and history. By investigating its surface and core samples in greater detail, scientists aim to unlock secrets about the early solar system and, by extension, the formation of Earth. Additionally, the moon serves as an ideal testing ground for technologies and life support systems needed for missions further afield, making it a critical stepping stone for Mars exploration. Turning to Mars, the objectives grow even more tantalizing as the red planet offers not just scientific but existential questions about our place in the universe. Future missions, spearheaded by NASA, ESA, and private companies like SpaceX, aim to pave the way for human exploration of Mars. These missions will build on the foundations laid by robotic explorers like Curiosity and Perseverance, and they will focus on colonization prospects, such as developing habitats that can withstand Martian conditions, mastering in situ resource utilization, particularly extracting water and producing oxygen, and creating sustainable energy solutions. Scientifically, Mars missions prioritize the search for signs of past or present life, studying its climate and geology in fine detail, and understanding its history of atmospheric and surface changes. This will involve drilling deeper into the Martian surface and even returning samples to Earth for comprehensive analysis. These endeavors not only aim to answer fundamental questions about Mars, but also prepare humanity for living on another planet, potentially safeguarding the future of our species. Each step taken on these celestial bodies serves as a giant leap toward becoming an interplanetary civilization, driven by the spirit of exploration and the quest for knowledge. Space telescopes like the Hubble Space Telescope and the James Webb Space Telescope have revolutionized our understanding of the cosmos, providing unparalleled views and insights that ground-based observatories simply cannot achieve. Since its launch in 1990, the Hubble Space Telescope has peered deep into space with its sensitive instruments, capturing breathtaking images of galaxies, nebulae, and distant stars. Hubble's observations have led to significant discoveries, such as the accelerated expansion of the universe, confirmed through its detailed studies of distant supernovae and the measurement of the redshifts of faraway galaxies. These findings have profound implications, leading to the theorization of dark energy as a driving force behind this expansion. Hubble's high-resolution imagery has been instrumental in refining our understanding of the life cycles of stars and the process of galaxy formation and evolution. By capturing detailed images of the early universe, Hubble has enabled astronomers to study the formation of the first galaxies and stars, shedding light on the conditions that prevailed shortly after the Big Bang. Its ability to observe in ultraviolet, visible, and near-infrared wavelengths allows scientists to investigate various celestial phenomena across a broad spectrum, making it a versatile tool for a wide range of astronomical research. The James Webb Space Telescope, launched in December 2021, is set to extend these capabilities even further. James Webb primarily operates in the infrared spectrum, allowing it to peer through dense cosmic dust clouds that obscure visible light, offering unprecedented views of the universe's earliest structures. One of James Webb's key objectives is to observe the first light-emitting objects that formed in the universe, investigating the formation and evolution of the earliest galaxies. Its advanced instruments will also enable scientists to study the atmospheres of exoplanets in exquisite detail, hunting for signs of potentially habitable conditions or even biosignatures that could indicate the presence of life. Moreover, James Webb will provide unparalleled insights into the process of star and planet formation, closely examining the molecular clouds where new stars and planetary systems are born. By capturing high-resolution spectra, James Webb will be able to analyze the chemical compositions of these regions, deepening our understanding of how the building blocks of planets and potentially life itself arise. Together, Hubble and James Webb represent a dynamic duo of space telescopes, each equipped with unique capabilities that complement one another, vastly expanding our knowledge of the universe and positioning humanity on the cusp of new astronomical frontiers. Dark matter, an enigmatic and unseen component of the universe, plays a pivotal role in the cosmic tapestry, though it does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred through its gravitational effects on visible matter and the large-scale structure of the cosmos. Dark matter makes up about 27% of the universe's total mass energy content, vastly outnumbering the ordinary baryonic matter that forms stars, planets, and galaxies, which accounts for only about 5%. The remaining 68% constitutes dark energy, a mysterious force driving the accelerated expansion of the universe. The discovery of dark matter's importance dates back to the 1930s, when astronomer Fritz Zwicky observed that the galaxies in the Coma cluster were moving much faster than they should, given the visible mass of the cluster. Later, in the 1970s, Vera Rubin's work on the rotation curves of spiral galaxies provided compelling evidence. The outer regions of galaxies were rotating at speeds that could not be explained by the mass of the visible stars and gas alone. This suggested the existence of a significant amount of unseen mass, or dark matter, providing the necessary gravitational pull. In cosmology, dark matter is crucial for several reasons. First, it serves as the scaffolding for structure formation in the universe. In the early universe, dark matter clumped together under the influence of gravity, forming the cosmic web structure that acts as a foundation for galaxy formation. Without dark matter, galaxies, clusters, and superclusters would not have formed in the way we observe them today. Secondly, dark matter helps us understand gravitational lensing, where the gravitational field of a massive object, like a galaxy cluster, bends the light from objects behind it. This bending effect reveals regions of dark matter, allowing us to map its distribution in the universe. Finally, understanding dark matter is essential for a complete theory of fundamental physics. While several candidates such as weakly interacting massive particles and axions have been proposed, definitive detection and identification of dark matter particles remain elusive. Unlocking the nature of dark matter could bridge gaps in the standard model of particle physics and offer insights into the universe's most profound mysteries. Dark matter is a cornerstone in our quest to comprehend the cosmos, intertwining the realms of cosmology, astrophysics, and particle physics. Dark energy, the mysterious force driving the accelerated expansion of the universe, stands as one of the most profound enigmas in modern cosmology. First inferred from observations of distant supernovae in the late 1990s, dark energy constitutes about 68% of the universe's total mass energy content. Unlike dark matter, which exerts gravitational pull, dark energy seems to work in opposition to gravity, causing the expansion of the universe to accelerate rather than slow down. Scientists study dark energy primarily through observational cosmology, employing several key methods. One pivotal approach involves the use of Type 1a supernovae as standard candles. Due to their consistent intrinsic brightness, these exploding stars can be used to measure astronomical distances accurately. By comparing the observed brightness of these supernovae to their redshifts, an indication of how much the universe has expanded since the light left the supernova, researchers discovered that galaxies are moving away from each other at an accelerating rate. This surprising finding suggested the presence of an unknown force counteracting gravity, which came to be known as dark energy. Another method involves studying the cosmic microwave background radiation, the afterglow of the Big Bang. Detailed measurements of the cosmic microwave background, particularly by missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have provided a wealth of information about the universe's early conditions and its subsequent evolution. Variations in the cosmic microwave background reveal information about the universe's geometry, composition, and expansion history, highlighting the role of dark energy in shaping cosmic evolution. Large-scale structure surveys also play a crucial role in theorizing about dark energy. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey map the distribution of galaxies across vast distances, allowing scientists to study how cosmic structures have evolved over time. Baryon acoustic oscillations, which are regular periodic fluctuations in the density of visible baryonic matter of the universe, serve as a ruler for measuring the scale of cosmic structures. Observing baryon acoustic oscillations helps scientists understand how dark energy influences the rate of expansion at different epochs in the history of the universe. On the theoretical side, dark energy spurs a rich dialogue within the field of fundamental physics. One leading theory is that dark energy is a property of space itself, encapsulated by the cosmological constant, lambda, in Einstein's equations of general relativity. Alternatively, some theories propose that dark energy is a dynamic field, sometimes called quintessence, which evolves over time. There are also more exotic theories involving modifications to gravity at cosmic scales. These diverse approaches, combining observational data with theoretical models, provide a multifaceted understanding of dark energy, even though its true nature remains elusive. As ongoing and future missions like the Euclid Telescope and the Wide Field Infrared Survey Telescope aim to gather more detailed observational data, scientists hope to unlock further secrets of this cosmic puzzle, bringing us closer to a complete understanding of the forces shaping our universe. Gravitational waves are ripples in the fabric of space-time, created by some of the universe's most violent and energetic processes. These waves were first predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. According to Einstein's theory, massive objects that accelerate, such as binary neutron stars, black holes, or supernovae, disturb space-time, generating waves that propagate outward at the speed of light, carrying energy away from the source. The first direct detection of gravitational waves was finally achieved almost a century later on September 14th, 2015, by the Laser Interferometer Gravitational Wave Observatory. This landmark event marked a revolutionary moment in astrophysics. LIGO's detection confirmed the presence of gravitational waves and provided a new way to observe the cosmos, independent of traditional electromagnetic radiation, light. LIGO detects gravitational waves using a technique called laser interferometry. The observatory features two identical facilities located in Livingston, Louisiana, and Hanford, Washington. Each facility has two long arms, each stretching 4 kilometers, about 2.5 miles, arranged in an L shape. A high-powered laser splits into two beams that travel down these arms and reflect off mirrors at the ends, creating an interference pattern. When a gravitational wave passes through Earth, it stretches and compresses space, causing tiny changes in the distance between the mirrors. These minute changes, on the order of 1,000th of the diameter of a proton, alter the interference pattern, signaling the presence of a gravitational wave. The first detected event, called GW 50914, originated from the merger of two black holes, roughly 1.3 billion light-years from Earth. The black holes, with masses about 29 and 36 times that of the Sun, spiraled together and eventually coalesced to form a single, more massive black hole. This cataclysmic event released a staggering amount of energy in the form of gravitational waves, confirming the existence of binary black hole systems and providing direct evidence for their mergers. This groundbreaking detection opened a new window into the universe, allowing scientists to probe phenomena that were previously invisible. Gravitational wave astronomy has since expanded with multiple detections, including neutron star mergers, which in one instance, GW 170817, were observed in both gravitational waves and electromagnetic signals, inaugurating a new era of multi-messenger astronomy. Continued advancements, including upgrades to LIGO and the addition of other detectors like Virgo in Italy and Kagra in Japan, promise an even deeper understanding of the universe, potentially uncovering unknown astrophysical processes and providing insights into the fundamental nature of gravity itself. Fast radio bursts and other enigmatic astronomical signals are some of the most perplexing phenomena in modern astrophysics, challenging our understanding of the universe in profound ways. Fast radio bursts are extremely brief but powerful bursts of radio waves, lasting only a few milliseconds, yet during that fleeting moment, each fast radio burst can emit as much energy as the sun does in an entire day. The first fast radio burst was discovered in 2007, and since then, dozens have been identified, each raising more questions than answers about their origins and mechanisms. One of the primary challenges posed by fast radio bursts is pinpointing their exact origins. While some fast radio bursts are one-time events, others, like FRB 121102, have been observed to repeat. This distinction suggests that there may be multiple types of sources or mechanisms generating these bursts. The discovery of repeating fast radio bursts has led to some breakthroughs, such as localizing one particular repeating source to a star-forming region in a dwarf galaxy about 3 billion light-years away. This localization provides valuable clues, but still leaves many hypotheses on the table, ranging from highly magnetized neutron stars, magnetars, and collapsing black holes, to more exotic scenarios involving extraterrestrial civilizations employing powerful energy sources. Another enigmatic signal challenging our cosmic understanding, is the WOW signal detected in 1977 by the Big Ear Radio Telescope. This intense, non-repeating narrowband radio signal bore the hallmarks of an artificial origin, prompting speculation about intelligent extraterrestrial communication. Despite several follow-up efforts, no similar signals have been detected, leaving its origins a tantalizing mystery. These unexplained signals push the boundaries of our current astrophysical theories and observational capabilities. For instance, studying fast radio bursts has the potential to enhance our understanding of the intergalactic medium. As radio waves travel through space, they interact with electrons, causing dispersion or a delay in arrival times of different frequencies. By analyzing this dispersion, scientists can gain insights into the density and distribution of intergalactic matter, providing a new tool to probe the cosmos on a large scale. Furthermore, the study of these mysterious signals necessitates the development of more sophisticated detection methods and instruments. Radio telescopes like CHIME, Canadian Hydrogen Intensity Mapping Experiment, and ASCAP, Australian Square Kilometre Array Pathfinder, are leading the charge in monitoring the sky for these elusive bursts, increasing the detection rate and providing a more detailed catalog of fast radio bursts. These advancements, in turn, drive technological progress in radio astronomy and data analysis techniques. In sum, fast radio bursts and other mysterious cosmic signals are not only fascinating phenomena, but also serve as catalysts for scientific and technological advancement, expanding our understanding of the universe and potentially unveiling new aspects of the fundamental physical principles that govern it. The exploration of these enigmatic signals continues to be a frontier of astrophysical research, promising future breakthroughs that could reshape our comprehension of the universe. The concept of parallel universes and the multiverse is one of the most tantalizing and speculative theories in modern cosmology and theoretical physics, suggesting that our universe might be just one of many distinct and possibly infinite universes. Several leading theories propose the existence of these parallel worlds, each hinging on different aspects of physics and cosmology. One of the primary theories is the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. According to the many worlds interpretation, every quantum event that has multiple possible outcomes results in the universe splitting into several branches, each representing a different outcome. For example, if a particle has a 50-50 chance of being in one of two states, the universe would split into two, with each branch realizing one of the states. This multiplicity would imply that every possible outcome of every event is realized in some world, leading to an enormous, possibly infinite number of parallel universes where every conceivable history and future exists. Another compelling notion comes from inflationary cosmology, particularly the theory of eternal inflation formulated by physicist Alan Guth and others. This theory posits that the rapid expansion of space, or cosmic inflation that occurred shortly after the Big Bang, didn't stop uniformly. Instead, while some regions of space stopped inflating and formed distinct universes like ours, other regions continued to inflate. This process results in a multiverse of bubble universes, each with possibly different physical properties and constants. These bubble universes could never interact with each other, making their detection incredibly challenging, but suggesting a diverse array of parallel realities existing within a larger inflating space. String theory, another fundamental framework in theoretical physics, introduces the concept of a landscape multiverse. According to string theory, our universe might be one of many possible configurations of strings, with each configuration corresponding to a different vacuum state and fundamental constants. This multitude of configurations forms a landscape where numerous universes exist, each governed by different physical laws. These universes within the string theory landscape could have different dimensions, particle types, and interactions, leading to a rich and varied multiverse. Furthermore, the idea of a brain multiverse emerges from certain interpretations of string theory and M theory. In this scenario, our universe is a three-dimensional brain floating in a higher dimensional space. Other brains could exist parallel to ours, each representing a different universe. Occasionally, these brains might interact or even collide, potentially explaining cosmic events like the Big Bang in our own universe. These theories of parallel universes and the multiverse, though highly speculative, provide intriguing possibilities for the nature of reality, suggesting that our universe might be only one facet of a much grander and more complex cosmos. Scientists and philosophers alike grapple with the profound implications of these ideas, pondering questions about existence, reality, and the ultimate nature of the universe. While empirical evidence for parallel universes remains elusive, advancements in theoretical models and observational techniques may one day offer more concrete insights into these fascinating realms. Studying and interpreting cosmic phenomena like quasars and blazars involves a combination of multi-wavelength observations, sophisticated theoretical models, and advanced computational techniques. These enigmatic objects, powered by supermassive black holes at the centers of galaxies, illuminate some of the most energetic processes in the universe. Quasars, short for quasi-stellar objects, are incredibly luminous. They were first identified as strong radio sources in the 1960s, but were later found to emit across the electromagnetic spectrum, including visible light, ultraviolet, infrared, X-rays, and even gamma rays. Quasars derive their extraordinary luminosity from the accretion of material into the supermassive black hole at their core. As matter spirals into the black hole, it forms an accretion disk where gravitational energy is converted into electromagnetic radiation. These emissions can outshine the entire host galaxy, making quasars visible over vast cosmic distances and thus crucial probes for the high redshift universe. Blazars are a specific subset of quasars distinguished by their jets pointing almost directly toward Earth. This orientation results in relativistic beaming, where the jet's light is intensified, making blazars appear extremely bright and variable. Blazars are further categorized into BL Lacertae objects and flat-spectrum radio quasars, based on their emission characteristics. The study of blazars helps in understanding the physics of jet formation, particle acceleration, and the interaction of jets with the interstellar medium. To study these cosmic phenomena, astronomers use a suite of observational tools that span the entire electromagnetic spectrum. Radio telescopes, such as those employed in the Very Large Array or the Atacama Large Millimeter/Submillimeter Array, capture the radio emissions of quasars and blazars, providing insights into the structure and dynamics of their jets. Optical and ultraviolet observations from ground-based observatories and space telescopes like the Hubble Space Telescope help analyze the light from the accretion disk and the surrounding regions. X-ray observatories like Chandra and gamma-ray telescopes, such as the Fermi Gamma-Ray Space Telescope, explore the high-energy emissions, offering clues on particle acceleration mechanisms and energy dissipation processes in jets. Spectroscopic analysis plays a crucial role in interpreting the data. By examining the spectra of quasars and blazars, scientists can determine the redshift, which reveals their distance and the rate of the universe's expansion at different epochs. Spectroscopy also uncovers the chemical composition, velocity, temperature, and density of the emitting and absorbing material. helping to model the physical conditions near the supermassive black hole. Theoretical models and numerical simulations complement observational data by providing frameworks to understand and predict the behavior of quasars and blazars. These models simulate the dynamics of accretion disks, magnetic fields, jet formation, and radiative processes, enabling a deeper understanding of the underlying physics. The synergy between observation and theory helps unravel the complex mechanisms driving these phenomena, shedding light on the life cycle of galaxies, the growth of black holes, and the evolution of the universe itself. By investigating quasars and blazars, scientists not only learn about these extraordinary cosmic beacons, but also gain broader insights into the fundamental processes shaping the cosmos, from the formation of structures in the early universe to the energetic feedback mechanisms influencing galaxy evolution. Astrobiology is the branch of science dedicated to the study of life beyond Earth, intertwining disciplines like biology, chemistry, physics, and astronomy. Scientists in this field seek to understand the origins, evolution, distribution, and future of life in the universe. One of the intriguing aspects of astrobiology is its quest to answer fundamental questions. Are we alone in the universe? How do life forms adapt to extreme environments? To tackle these questions, researchers investigate both Earth-based and extraterrestrial environments, focusing on places where life as we know it could potentially exist. Exploring our solar system, astrobiologists examine Mars's surface chemistry, the icy moons of Jupiter such as Europa, and Saturn's moon Enceladus, both of which have subsurface oceans that may harbor microbial life. Advanced techniques such as spectroscopy help detect potential biomarkers in the atmospheres of distant exoplanets, planets orbiting stars beyond our solar system. These studies often leverage data from cutting-edge telescopes, rovers, and space probes. Simultaneously, laboratory experiments simulate extraterrestrial conditions, thus offering insights into how organisms might survive extreme environments ranging from the vacuum of space to the high radiation on Mars. By studying extremophiles on Earth, organisms thriving in hot springs, deep-sea vents, and radioactive waste, astrobiologists gain valuable clues about life's resilience and adaptability, paving the way for future discoveries in the unfathomably large expanse of the cosmos. Extremophiles are microorganisms that thrive under extreme conditions, considered hostile to most forms of life. These remarkable organisms have adapted to environments with extreme temperatures, acidity, salinity, and radiation, thereby expanding our understanding of the potential for life beyond Earth. By studying extremophiles, scientists glean critical insights into where and how to search for extraterrestrial life. For instance, bacteria enduring scorching heat in hydrothermal vents on the ocean floor, or microbes surviving in radioactive waste or highly acidic environments reveal the astonishing adaptability of life. This knowledge directs astrobiologists to focus on similar extreme environments elsewhere in the solar system and beyond. Take, for example, the acid-loving extremophiles found in sulfuric hot springs. These organisms inform the study of Mars, where sulfur compounds are prevalent, suggesting that if life ever existed there, it might resemble these hardy Earth bacteria. Additionally, the discovery of extremophiles thriving in ice shells or beneath the permafrost hints at potential life in the icy moons of Jupiter and Saturn, such as Europa and Enceladus. These moons possess subsurface oceans heated by tidal forces, creating an environment where extremophiles may thrive. Furthermore, researchers use extremophiles to develop biosignature detection methods, aiming to identify chemical signs of life in the atmospheres of exoplanets. By understanding the metabolic and chemical processes extremophiles use to survive, scientists improve their criteria for detecting life forms in the most unearthly of habitats, thereby guiding future missions and enhancing the search for life in the universe. One of the most promising places to find microbial life in our solar system is Mars. The red planet has long intrigued scientists due to its past evidence of liquid water essential for life as we know it. Recent discoveries of seasonal methane plumes and recurring slope linea, dark streaks on the surface, suggest that liquid water might occasionally flow today. Methane, in particular, holds interest because it can be produced by biological processes, although geological processes can also account for its presence. Additionally, the detection of complex organic molecules by the Curiosity rover in Gale Crater has bolstered the idea that Mars could have harbored microbial life in its ancient history, and possibly still does in subsurface niches. The icy moons of Jupiter and Saturn, specifically Europa and Enceladus, are also top contenders in the search for microbial life. Europa's thick icy crust covers a global ocean of liquid water kept warm by the tidal forces exerted by Jupiter. Observations from the Galileo spacecraft and more recently the Hubble Space Telescope have detected potential plumes of water vapor erupting from Europa's surface, hinting at a dynamic subsurface ocean that could harbor life. Enceladus, Saturn's moon, has captured scientific fascination due to its spectacular geysers, ejecting water vapor, organic molecules, and even salts into space from its south pole. The presence of these plumes, combined with evidence of hydrothermal activity on the seafloor of Enceladus's subsurface ocean, make it another prime candidate for microbial life. These environments provide not only the liquid water, but also the energy and chemical building blocks necessary for life, making them key targets for future exploratory missions. Missions like the search for life on Mars play a pivotal role in advancing the field of astrobiology by directly exploring environments that might once have been or still could be habitable. The rovers and orbiters sent to Mars are equipped with sophisticated instruments designed to analyze the planet's geology, climate, and potential biosignatures. For example, NASA's Perseverance rover, which landed in 2021, is meticulously studying Jezero Crater, a site believed to have once housed a river delta and lake, by examining sedimentary rocks known to trap and preserve organic molecules. Perseverance aims to uncover signs of ancient microbial life. These missions provide invaluable data about past water activity, organic chemistry, and other conditions that could support life, thus directly informing our understanding of planetary habitability. Furthermore, the technology and methodologies developed for Mars missions have broad implications for astrobiology. Instruments like the sample analysis at Mars on the Curiosity rover can detect a range of organic compounds and measure isotopic ratios, providing clues about the planet's ancient environment and its capacity to support life. These techniques are vital for interpreting potential biosignatures, not just on Mars, but also on other celestial bodies. Moreover, the insights gained from Mars missions contribute to the development of new technologies for future explorations, such as Europa Clipper, which will assess the habitability of Europa, and the Dragonfly mission to Titan. Each mission refines our understanding of where and how to look for life, enhancing our comprehension of life's potential existence elsewhere in the cosmos, and reinforcing the interconnected nature of astrobiological research. The discovery of life beyond Earth would hold profound implications for our understanding of biology, the origins of life, and our place in the universe. Firstly, it would fundamentally alter our concept of life's uniqueness and adaptability. Finding even the simplest microbial life forms elsewhere would demonstrate that life is not confined to Earth's unique conditions and may arise in a variety of environments. This could support the hypothesis that life might be more common throughout the cosmos than previously thought. Such a discovery would prompt scientists to rethink the conditions deemed necessary for life and expand their search to include a broader range of environments. Moreover, discovering extraterrestrial life would carry significant philosophical, cultural, and potentially theological impacts. It would challenge long-held human-centric views of the universe, sparking new discussions and potentially reshaping humanity's sense of identity and purpose. What would it mean if we are not alone? Philosophers, religious leaders, and the general public would engage in deep, reflective debates on our relationship with the cosmos and our responsibilities as stewards of Earth. Additionally, the search for and potential discovery of extraterrestrial life would likely stimulate advancements in science and technology, much as the space race did in the mid-20th century. Enhanced technological innovation to support space missions could lead to myriad benefits for life on Earth, from new materials to improvements in communication and data analysis technologies. Finding life beyond Earth would not only redefine our understanding of biology, but also profoundly influence our culture, technology, and worldview. Scientists deploy several innovative strategies to search for biosignatures on exoplanets, leveraging cutting-edge technology and a comprehensive understanding of life's indicators. Central to this quest is the use of powerful space telescopes equipped with advanced instruments capable of analyzing the light from distant stars and their orbiting planets. The James Webb Space Telescope, for instance, is designed to detect chemical signatures in the atmospheres of exoplanets by analyzing the light that passes through them during a transit. By studying the absorption lines in the spectrum, scientists can identify molecules such as oxygen, methane, and water vapor compounds that could suggest biological processes. Additionally, upcoming missions like the European Space Agency's Ariel Atmospheric Remote Sensing Infrared Exoplanet Large Survey aim to survey a diverse range of exoplanetary atmospheres. Scientists also employ the method of direct imaging, using advanced techniques to block out the overwhelming light from a planet's host star, thereby allowing the faint light reflected off the planet to be studied. This method can reveal surface features and atmospheric compositions, potentially identifying biosignatures like chlorophyll or other pigments associated with photosynthesis. Ground-based observatories, such as the extremely large telescope currently under construction in Chile, will complement space-based efforts by providing high-resolution imaging and spectroscopy capabilities. These observatories will enable detailed studies of exoplanetary atmospheres and surfaces, looking for anomalies like an unexpected abundance of specific gases or surface colors that might indicate biological activity. Through these multifaceted efforts, scientists aim to systematically search for the telltale signs of life across the galaxy, deciphering the myriad ways life might manifest in the diverse environments of distant exoplanets. The prospect of human colonization of Mars is both exciting and formidable, presenting unprecedented challenges and opportunities. As the principal focus of several space agencies and private companies, Mars represents the most feasible target for human colonization due to its relative proximity to Earth and the intriguing possibility of utilizing its resources. NASA, SpaceX, and other entities are actively developing technology and strategies to enable sustainable human presence on the Red Planet. NASA's Artemis program, aiming to return humans to the Moon, is considered a stepping stone to Mars, where plans involve leveraging lunar missions to test critical technologies and systems. SpaceX, spearheaded by Elon Musk, is ambitiously working on the Starship, a spacecraft designed to ferry humans and cargo to Mars. One of the key elements of making Mars habitable revolves around the concept of in situ resource utilization, which involves harnessing local Martian resources to produce water, oxygen, and building materials. Mars's atmosphere, rich in carbon dioxide, can be used to produce oxygen through electrolysis, while its regolith could provide materials for constructing habitats. However, immense challenges remain, including radiation protection since Mars lacks a magnetic field and thick atmosphere to shield its surface from cosmic rays and solar radiation. Ensuring the psychological and physiological well-being of astronauts during the long-duration missions and on Mars itself is another critical concern. Moreover, the development of life support systems, reliable communication networks, and sustainable food production methods are essential for the success of human colonies on Mars. Research on Earth with closed-loop systems, like those being tested in extraterrestrial analogs such as the HIC's habitat in Hawaii, aim to simulate and solve these challenges before humans set foot on the Martian surface. While the technological and logistical hurdles are significant, the progress made in recent years underlines a growing optimism. The dream of creating self-sufficient colonies on Mars is driven by a blend of scientific curiosity, technological innovation, and the enduring human spirit of exploration and survival. Space agencies around the world are meticulously developing strategies to address the myriad challenges associated with long-duration space travel, which are crucial for missions to destinations like Mars and beyond. One of the most pressing concerns is the health and well-being of astronauts during extended periods in microgravity. Prolonged exposure to zero gravity can lead to muscle atrophy and bone density loss. To mitigate these effects, agencies like NASA and ESA have designed advanced exercise regimes and specialized equipment, such as resistive exercise devices, to help maintain astronauts' physical health. In addition, research on artificial gravity, potentially through rotating sections of spacecraft, is being explored as a long-term solution to combat the deleterious effects of weightlessness. Radiation exposure is another significant challenge, as space travelers face heightened levels of cosmic rays and solar radiation once they leave the protective bubble of Earth's magnetosphere. Spacecraft shielding is under continuous improvement, utilizing materials that can better absorb or deflect harmful radiation. NASA, for example, is investigating the use of water or polyethylene shielding alongside innovative concepts like magnetic fields to create a protective force field around the craft. Advances in medical technologies, such as telemedicine and compact medical kits that can handle a range of health issues, are also critical. These systems need to ensure that astronauts receive timely medical care, even when millions of kilometers from Earth. Psychological resilience is equally pivotal, as astronauts must cope with isolation, confinement, and the stress of long missions. Agencies are addressing mental health through rigorous pre-flight psychological training, the design of spacecraft with more livable interiors, and continuous in-flight support, including virtual reality experiences to mimic aspects of earthly environments. Communication delays, inevitable on long missions, are managed through the development of autonomous systems and artificial intelligence aboard spacecraft, enabling crews to conduct operations independently should immediate communication with mission control be impossible. By integrating technological advancements, rigorous training programs, and innovative research, space agencies are shaping a multifaceted approach to tackle the complexities of long-duration space travel, paving the way for humankind's exploration of the final frontier. Private companies like SpaceX are playing an increasingly pivotal role in the future of space exploration, revolutionizing the industry with their innovative technologies, cost-effective solutions, and ambitious goals. Historically, space exploration was dominated by government space agencies such as NASA, Roscosmos, and ESA. However, the entry of private companies has introduced a new era of commercial spaceflight, characterized by rapid advancements and reduced costs. SpaceX, for instance, has made significant strides in developing reusable rocket technology, which has drastically cut the expenses associated with launching payloads into space. The Falcon 9 rocket, known for its ability to return and land after delivering its cargo, exemplifies this breakthrough, enabling more frequent and economical missions. One of the most notable contributions of SpaceX and other private companies is their role in facilitating missions to the International Space Station and beyond. SpaceX's Dragon spacecraft has been instrumental in transporting supplies and crew to the International Space Station under NASA's Commercial Crew Program. This partnership not only alleviates the logistical burden on NASA, but also allows the agency to focus more resources on deep space exploration, including Mars and lunar missions. Additionally, SpaceX's ambitious Starship project aims to develop a fully reusable spacecraft capable of transporting humans to Mars, thus aligning with long-term goals of planetary colonization and interplanetary travel. Such endeavors are pushing the boundaries of what's possible, accelerating the timeline for human exploration of other celestial bodies. Moreover, the involvement of private companies fosters a competitive and collaborative space economy, spurring innovation across the industry. With initiatives like SpaceX's Starlink project, aimed at providing global satellite internet coverage, and Blue Origin's efforts to develop space tourism and lunar landers, the landscape of space exploration is rapidly diversifying. These ventures not only advance technological capabilities, but also inspire public interest and investment in space endeavors. Private companies are transforming space exploration from a government-led enterprise into a dynamic and multifaceted industry, driving progress through innovation, efficiency, and visionary projects that bring humanity closer to becoming an interplanetary species. Space tourism is poised to develop rapidly over the coming decades, driven by advancements in technology, increasing private sector involvement, and a growing public interest in experiencing space firsthand. Initial forays into space tourism have already begun, with companies like SpaceX, Blue Origin, and Virgin Galactic leading the charge. These companies have each developed unique approaches to making space more accessible. Virgin Galactic, for instance, offers suborbital flights that allow participants to experience several minutes of weightlessness and stunning views of Earth from the edge of space. Blue Origin's New Shepard rocket provides a similar experience, featuring a fully automated system designed to carry tourists to the Kármán line, the boundary of space. In the future, space tourism is expected to expand beyond brief suborbital trips to encompass longer and more immersive experiences. Within the next few decades, orbital tourism may become a reality, with private companies offering stays aboard space stations or habitats. These space hotels could provide guests with the opportunity to live and work in microgravity, conduct scientific experiments, and enjoy spectacular views of Earth from orbit. Companies like Axiom Space are already planning commercial modules for the International Space Station, which could later become standalone space habitats. Additionally, ambitious projects such as SpaceX's Starship envision taking tourists on circumlunar trips around the Moon, providing a truly out-of-this-world experience. As technology advances and the cost of launching and sustaining human presence in space decreases, space tourism could eventually extend to lunar or even Martian surfaces. Future developments might see the construction of bases or colonies, offering travelers the chance to explore extraterrestrial landscapes and participate in the early stages of space colonization. This progression will likely be supported by innovations in life support systems, habitat construction, and in situ resource utilization, ensuring that such ventures are both safe and sustainable. Ultimately, the growth of space tourism will not only open new frontiers for human exploration and recreation, but also fuel technological innovations and foster a greater global interest in space science, bringing humanity closer to its dream of becoming a multiplanetary species. Asteroid mining presents a tantalizing range of potential benefits, balanced by significant risks that must be carefully managed. On the benefit side, asteroids are rich in valuable resources including metals like iron, nickel, and cobalt, as well as precious metals such as platinum and gold. These materials are essential for various industries on Earth, particularly in electronics and renewable energy technologies. Mining asteroids could alleviate the strain on Earth's resources and reduce the environmental impact associated with terrestrial mining operations. Additionally, certain asteroids contain water, which can be broken down into hydrogen and oxygen to provide fuel for deep space missions, potentially enabling a more sustainable and cost-effective exploration of the solar system. Asteroid mining also holds the promise of stimulating economic growth and technological innovation. The development of new mining techniques and space travel technology could drive advancements that benefit other sectors, such as robotics, artificial intelligence, and material science. The commercial viability of asteroid mining could create new markets and job opportunities, fostering a space-based economy that supports further exploration and utilization of space resources. By securing a supply of critical raw materials, asteroid mining could also bolster national security and contribute to economic stability, reducing dependency on geopolitically sensitive terrestrial sources. However, these potential benefits are tempered by substantial risks and challenges. The technical and logistical challenges of asteroid mining are formidable, encompassing everything from identifying and reaching suitable asteroids to developing efficient extraction and processing techniques. The harsh environment of space, with its extremes of temperature, radiation, and microgravity, adds additional layers of complexity. Moreover, the economic viability of such ventures remains uncertain given the high costs of space missions and the current lack of infrastructure to support large-scale mining operations. Legal and ethical considerations also loom large. The international regulatory framework governing space activities, primarily the Outer Space Treaty of 1967, is ambiguous regarding the ownership and exploitation of extraterrestrial resources. This uncertainty could lead to conflicts between nations and private entities over resource rights and environmental impacts. Furthermore, the potential environmental consequences of mining activities, such as the disruption of celestial bodies and the accumulation of space debris, pose long-term risks to the orbital environment and future space missions. Asteroid mining offers significant opportunities to revolutionize resource acquisition and spur technological and economic growth. However, realizing these benefits requires overcoming substantial technical, economic, legal, and ethical challenges. Thoughtful and collaborative approaches will be necessary to balance the promise of space resource utilization with the need to protect and preserve the space environment for future generations. International collaborations play a crucial role and shaping the future of space exploration, fostering a spirit of cooperation, pooling resources, and distributing risk among participating nations. The complexities and costs associated with space missions are substantial, and no single nation, regardless of its technological prowess or economic strength, can easily shoulder these burdens alone. By collaborating, countries can share the expenses and technical challenges, making ambitious projects more feasible and accelerating scientific advancements. The International Space Station is a prime example of such collaboration, involving the United States, Russia, Japan, Canada, and the European Space Agency. This floating laboratory has become a symbol of international partnership, enabling scientific research that benefits all of humanity. Beyond the International Space Station, collaborative missions like the James Webb Space Telescope, jointly developed by NASA, ESA, and the Canadian Space Agency, illustrate how shared efforts can lead to groundbreaking discoveries. These partnerships enable the sharing of knowledge, skills, and technology, enhancing the overall capabilities of the global space community. International collaboration also extends to planetary exploration, as seen in missions like ExoMars, a joint endeavor by ESA and Roscosmos aimed at searching for signs of life on Mars. Such missions benefit from the diverse expertise and perspectives that each contributing nation brings, leading to more robust planning, data analysis, and problem-solving skills. Moreover, international collaborations help to build and strengthen geopolitical relationships. The cooperation required for joint missions fosters trust and can serve as a platform for diplomacy, easing tensions between countries. This cooperative approach also promotes the idea of space as a shared domain, where the achievements and benefits of exploration are accessible to all. The Artemis Accords, led by NASA, exemplify this spirit by establishing a framework for international collaboration on lunar exploration, aiming for the sustainable, peaceful, and transparent use of the Moon's resources. However, challenges remain. The differing priorities, regulations, and policies of participating nations can lead to complex negotiations and coordination efforts. Intellectual property rights, data sharing, and the distribution of roles and responsibilities require careful management. Despite these challenges, the benefits of international collaboration in space exploration far outweigh the hurdles. By working together, nations can accomplish far more than they could individually, pushing the boundaries of human knowledge, exploring new frontiers, and ensuring that the exploration and utilization of space are conducted in a manner that benefits all of humanity. Meteor showers are celestial events that captivate observers with their dazzling displays of shooting stars, and some of the most spectacular ones occur annually. The Perseids, visible every August, are among the most famous and reliable meteor showers, known for their bright, fast meteors and high activity rates, often producing up to 60 meteors per hour at their peak. Originating from the debris left by Comet Swift-Tuttle, the Perseids have enchanted stargazers for centuries, creating a stunning night sky show that often includes fireballs, exceptionally bright meteors that stand out even amid the brilliance of their peers. Another notable meteor shower is the Geminids, which grace the December skies. Unlike many other meteor showers that originate from comets, the Geminids are linked to a rocky asteroid named 3200 Phaethon. This shower is known for its slow-moving, colorful meteors, sometimes in hues of yellow, blue, and green. At its peak, the Geminids can produce over 100 meteors per hour, making it one of the most prolific and reliable meteor showers, rewarding those who brave the chilly winter nights to observe the celestial fireworks. Meteor showers occur when the Earth passes through streams of cosmic debris left behind by comets or asteroids. as these small particles, often no bigger than grains of sand, enter the Earth's atmosphere at high speeds, frequently tens of miles per second. They vaporize due to friction with the atmospheric gases, creating brilliant streaks of light across the sky. Each meteor shower is named after the constellation from which its meteors appear to radiate, known as the radiant point. For example, the Perseids seem to radiate from the constellation Perseus, while the Geminids radiate from Gemini. The regularity and predictability of these events are due to the Earth's annual passage through these debris trails, which are maintained by the parent object's orbits around the Sun. This cosmic choreography ensures that year after year, these spectacular meteor showers provide a dependable and awe-inspiring spectacle, connecting us to the vast and dynamic universe beyond our planet. Auroras, also known as the Northern and Southern Lights, are among the most mesmerizing natural phenomena observed in the Earth's polar regions. These stunning light displays occur when charged particles emitted by the Sun, primarily electrons and protons, interact with the Earth's magnetic field and atmosphere. The Sun constantly emits a stream of charged particles known as the solar wind. When this solar wind reaches the Earth, most of the particles are deflected by the planet's magnetosphere, but some are funneled towards the polar regions where the magnetic field lines converge. The beautiful displays of light in auroras result from these charged particles colliding with atoms and molecules in the Earth's upper atmosphere, primarily in the thermosphere at altitudes between 60 and 300 miles. When these energetic particles strike the atmospheric gases, mainly oxygen and nitrogen, they excite these atoms and molecules, causing them to emit light as they return to their ground state. The specific colors seen in auroras depend on the type of gas and its altitude. Oxygen, for example, can produce green or red light, with green being more common at lower altitudes between 60 and 150 miles, and red appearing at higher altitudes above 150 miles. Nitrogen, on the other hand, typically emits blue or purplish red light. The overall dynamics that create auroras are influenced by solar activity, such as solar flares and coronal mass ejections, which can intensify the solar wind and inject even more charged particles into the Earth's magnetosphere. During periods of high solar activity, such as those associated with the solar cycle's peak, auroras are more frequent and can be seen at lower latitudes than usual. The resulting light shows can be both spectacular and unpredictable, with displays sometimes appearing as gently waving curtains, spirals, or even explosive bursts of light that can rapidly change in intensity and color. Auroras serve as a vivid reminder of the complex and dynamic interactions between the Sun and the Earth, and they underscore the broader connection within our solar system. Observers in regions such as Scandinavia, Canada, Alaska, and Antarctica often find themselves privileged to witness these natural light shows, which continue to inspire wonder and scientific inquiry alike. Cosmic events such as eclipses and transits offer some of the most awe-inspiring spectacles visible from Earth, drawing in the gaze of both amateur stargazers and seasoned astronomers. Solar eclipses are particularly remarkable, occurring when the moon passes between the Earth and the Sun, casting a shadow on our planet. There are different types of solar eclipses: total, partial, and annular. A total solar eclipse, where the moon completely covers the Sun, is a rare and breathtaking event that can plunge daytime into darkness and reveal the Sun's ethereal corona. These dramatic occurrences provide unique opportunities for scientific study, especially regarding solar atmospherics, helping to advance our understanding of solar phenomena. Lunar eclipses are equally captivating, occurring when the Earth comes between the Sun and the Moon, casting its shadow on the lunar surface. Unlike solar eclipses, lunar eclipses can be seen from anywhere on the nighttime side of the Earth and may last for a few hours. A total lunar eclipse, or blood moon, is particularly striking as the moon takes on a deep red hue caused by the scattering of sunlight through Earth's atmosphere, a process known as Rayleigh scattering. During these events, astronomers can study changes in the moon's environment and surface composition, while the general public enjoys a cosmic spectacle that has fascinated humans for millennia. Planetary transits, where a planet passes directly between the Earth and the Sun, provide another significant celestial event. The most famous of these are the transits of Mercury and Venus. During a transit, the planet appears as a small dark disk moving across the face of the Sun. These events are rare, with Mercury transits occurring approximately 13 to 14 times per century, while Venus transits happen in pairs separated by over a century. Transits are scientifically valuable as they help refine our understanding of the planet's orbits and have played historic roles in measuring astronomical units and calibrating our understanding of distances in the solar system. Additionally, conjunctions, where two celestial bodies appear very close to one another in the sky, are visually stunning and have astrological significance for many cultures. The Great Conjunction of Jupiter and Saturn, which occurs roughly every 2 decades, is particularly noteworthy. During these events, the planets align closely in the sky, providing a beautiful and symbolic display. Each of these cosmic events not only offers spectacular visual experiences, but also presents critical opportunities for scientific research. They enable astronomers to gather data on celestial mechanics, atmospherics, and solar and planetary characteristics, bridging the gap between the awestruck observer and the scientist, uniting humanity in a shared curiosity about the cosmos. Gamma-ray bursts and other high-energy phenomena have profoundly impacted our understanding of the universe, revealing the underlying dynamics of some of the most powerful and catastrophic events in cosmic history. Gamma-ray bursts are intense flashes of gamma radiation, the most energetic form of light, lasting from milliseconds to several minutes. They are typically classified into 2 types: short-duration gamma-ray bursts, which last less than 2 seconds and are thought to result from the merger of neutron stars, and long-duration gamma-ray bursts, which last longer and are usually associated with the collapse of massive stars forming black holes. The study of gamma-ray bursts has unveiled significant insights into star death, black hole formation, and the behavior of matter under extreme conditions. These bursts release more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. This immense release of energy provides a unique laboratory for studying relativistic physics and the mechanics of jet formation and propagation, as the gamma radiation often originates from highly relativistic jets emitted by these extreme events. By observing the afterglows of gamma-ray bursts across different wavelengths, from X-rays to optical and radio waves, astronomers can probe the environment around the burst, revealing information about the interstellar medium and even the host galaxy. Other high-energy phenomena, such as supernovae and active galactic nuclei, also play crucial roles in shaping our cosmic knowledge. Supernovae, the explosive ends of massive stars, not only distribute heavy elements throughout the universe, enriching the interstellar medium, but also serve as cosmic distance markers. Type 1a supernovae have been instrumental in measuring cosmic distances and led to the groundbreaking discovery of the universe's accelerating expansion, attributed to dark energy. This revelation has significantly influenced modern cosmological models and deepened the mysteries surrounding the nature of dark energy and the ultimate fate of the universe. Active galactic nuclei, powered by supermassive black holes at the centers of galaxies, emit vast amounts of high-energy radiation as they accrete matter. The study of active galactic nuclei has advanced our comprehension of black hole growth, galaxy evolution, and the interplay between central black holes and their host galaxies. Observations of active galactic nuclei across the electromagnetic spectrum, including gamma rays, X-rays, and radio waves, have elucidated processes such as accretion disk dynamics, relativistic jet formation, and the feedback mechanisms that regulate star formation in galaxies. The investigation of gamma ray bursts and other high-energy phenomena provides invaluable insights into some of the universe's most energetic events, shaping our understanding of stellar evolution, black hole physics, galaxy formation, and cosmology. These studies continue to push the boundaries of astrophysics, uncovering the fundamental processes that govern the universe and guiding future research in both observational and theoretical domains.